Es realmente una oportunidad de oro este curso y no solamente el curso, sino también el contacto con los Oldenburg. Realmente les pido, ¿cómo se llama? En forma de agradecimiento, un pequeño aplauso.
Well, it's a very great pleasure to be here. I didn't realize it until we arrived in this building on Friday, I guess it was, to just check out the surroundings. And we came into this auditorium, and I thought, oh, this is interesting, because I think I presented in a place that was somewhat similar to this. Because I was here in 2012 with an SEG Distinguished Lecture, but I kind of forgot everything about the surroundings. And then I walked in here and I thought, oh, I've taught in a building like this. And then the more I got down here, I realized this is the same auditorium. This is a really nice one. This is probably the nicest auditorium that we've seen, on our worldwide travels. So it's always a pleasure to be here. Also, it's a great pleasure to have everybody here this morning and perhaps all day. I hope all day. So this is the SEG DISC course. It stands for Distinguished Instructor Short Course, and it's on electromagnetics. And we're trying to kind of convey understanding of electromagnetics with the foundations and some applications. Before I start, there's two people that I really want to thank right from the bottom of my heart, because without the work of the people here, this just could not be happening. Oscar was amazing. He's the person who's, as far as a local host, has been more enthusiastic, worked harder on our behalf to try to get people to come than any place else that we've visited. So thank you, Oscar. The other person is Carlos Vargas. Carlos has been instrumental in having a group in Colombia be involved in this. And we're actually live streaming this to Colombia today. There's been, I think, 98 people that have registered in Colombia. They're incredibly enthusiastic, and it's all been because of Carlos. We were not able to bring the disc to Colombia this year just because of logistic reasons, but he's orchestrated all of that. So throughout the day, we might be making occasional offhand comments to, okay, are people in Colombia with us? Can understand us? Is everything working? But there are like close to 100 people out there that are being recipients of this live streaming. Before I start, I would really like to quickly go around the room and just find out who you are and what you're interested in, what your background is. It helps me a lot when we present things if we know a little bit about the background. So I'm just wondering if we could just quickly start, if we don't want to spend much time, but just quickly start to go around the room, and people could just tell me what you are, whether you're a student, professional, you're working with an oil company, or what it is that you're doing, so that I get an understanding of your background. So since Oscar's at the back, we'll start at the back. Oh, we'll need to pass that mic around, I think. Oh, is that?
Siempre aprender que soy soy investigador del Instituto de Geophysical y realmente me es muy placentero ver que me dieron muchos a este curso y espero que haya muchos puntos de este curso en los próximos años. La siguiente.
Hi, my name is Geophysical. I am doing my thesis at my
And your project, you're doing your thesis, your project is?
my project is
Electromagnetics?
Who is your advisor?
Matthias.
All right.
Good morning, my name is Abel. I am work in company, Geophysical. That's all.
What kind of geophysics?
The company is geology and geophysics integrated.
Integrated, okay.
Así es.
Okay.
Morning, my name is Rodrigo Rojas. I'm working in Institute Engineering.
Yeah, if you can also tell me what, like what kind of geophysics or what problems, we need to be real short. This is where-
Hello, my name is Eduardo. I'm doing my social service in Instituto de Física. I'm working with remote sensing, and I want to learn a lot about the electromagnetic fields and some software to apply this science. Thank you.
Good morning, my name is Rafael. I am a senior student from the physics, and I am interested in mining exploration. The physics applied to mining. Thank you.
Good morning, my name is Alex. I am student of physics, and I'm interested in hydrology, and I want to know what is the fundamentals of, what is the fundamentals that I have to apply in a hydrology. My name is Ángel Castañeda, and I'm a geophysical university.
My name is Fernanda. I'm a senior student.
Hello, my name is Ramon. I'm here because I want to know about about electromagnetics, and I want to apply in petroleum, maybe. I am with Sergio Tuck, and I here because he recommended me these course.
Hi, my name is Maria Guzman, and I'm a student of the degree of science. I was studying on campus and the course.
Good morning, my name is Francisco Juarez. I'm a physicist. And nowadays I'm doing my thesis project about information sources. And I'm very interested in the fundamental application of this in audio physics. That's why I'm here. Yes. Good morning. My name is Arturo. I'm a physicist. Right now I'm doing my thesis, my master's degree in physics conversion.
Hi, I'm Salvador Bautista. Currently, I'm working in exploration of minerals with a particular company.
My name is Pedro, and I'm a student, and I don't know what to do. Maybe, maybe all. I don't know. Yeah.
Hi, my name is Sandro. I'm here because electromagnetic methods are the future for research in resources.
maybe that will just work well. Pass it out this way.
Good morning. My name is Carlos Vasquez. I'm a student. I'm with Dr. Campos.
Hi, my name is Mara, and I'm very interested in electromagnetic exploration for different resources like thermic and hydrocarbons.
Hello, my name is Helime Aray. I'm research in geophysics in Venezuelan Foundation for Seismological Research. I would like to improve processing and interpretation in BPR data.
Hello, my name is Joaquin. I am also a student of the Universidad Michoacana San Nicolás de Hidalgo. I am working with passive seismic and magnetic methods for the construction of model of the conceptual the thermal resource.
Barely.
My name is I am
my name is Esteban Lopez. I am studying Mr.
Oscar's got a lot of students. Busy guy.
Hello, my name is Daniel Jimenez. I am a student. I am doing my thesis about self-potential and geothermal.
Hi, my name is Rafael Torres. I'm engineering geophysics. I'm working with Institute of Engineering in Geophysical.
Hello, my name is Aristóteles Carrillo. I'm here in order to learn about this, to apply in the technical engineering.
Hi, my name is Ivan, and I'm working with integration of passive seismic methods and electromagnetics for determining.
Hi, my name is Eric Acevedo. I am working in company in electrical methods.
Good morning. My name is Edgar. I am an earth science engineering student. I'm at my senior year, and my main interests are the thermal resources.
Good morning. My name is Ulises. I'm working in exploration.
Hi, good morning. My name is Luciano and I work in Manuales project.
Hi, my name is Alejandro and I work in Fine Company.
Wow, we got the Canolas group right here.
My name is Clemente. I work in Pinones. I am geophysics.
My name is Isaac. I'm a student. I started recently a project about geothermal energy. I'm interested in this course because electromagnetic methods are tiny part in geothermal exploration.
Hello, my name is Alejandro. I'm a student. I'm studying. Okay.
Hello, this is Rafael Colori. I'm a professional physicist. I work for Geotech Limited, and we do mainly airborne electromagnetic services. Thank you.
Hi, I am Silvia Martinez. I am geophysicist. I am full-time professor and researcher at the University of Sonora. I work with potential methods, resistivity, and transient electromagnetic methods.
Hi, my name is Natalia Silva. I study master degree in geology, and I work with potential methods.
Hi, my name is Sergio. I'm a physicist and currently I work at a private company, and I have been involved in the last years in the electromagnetic projects, more in the acquisition of great data, and well, it's always good to learn more and refresh knowledge.
Good morning, my name is Francisco Guante, and I'm working with engineering, and we are made a software about potentials, electromagnetics, transient electromagnetics, and we are going to start with the EMPI magnetologies.
I'm a teacher, I'm a researcher at the EMPI, and my main focus is control source electromagnetics. Beforehand, I worked for a while with these guys in GeoPhysical with magnetic tellurics and control source magnetic tellurics for mainly for geothermal applications.
Good morning, my name is Matthias Ducker. I'm a PhD student at the University of Bonn in Germany. And my PhD thesis, I did research into the modeling, scale modeling of IP responses of geological media, and I'm almost done. And I've already got my thesis. And here in Mexico, I'm doing different projects with electromagnetic methods.
Hi, my name is Carlos Chavelas. I'm studying geophysical engineering, and at this moment I'm taking a course to get my bachelor degree, and I'm very interested in learning a lot about electromagnetic.
Hi, my name is Sandra Esteves. I am a student for master, and I want to understand more about the electromagnetic models.
Good morning, my name is Pablo Aguirre. I'm a Master of Science student. I'm interested in signal processing.
Hi, my name is Andres Tejero. I am professor at Engineering Faculty of Earth Science Missions. And my field of interest is in user-friendly physics problems applying magnetic and electrical methods.
Hi, my name is Aide Lopez. I'm a student of my PhD with Dr. Tejero. Also, I teach electrical perspective here in engineering faculty, and I'm interested in use polarization method. And my thesis is about doing a program with two focus sources in one program. So that's all.
Good morning, my name is Manuel, and I'm doing my thesis in electromagnetic methods.
My name is Jose. I'm a physicist. My interest is oil and gas exploration. I was working on it recently for EMPI's research. My interests are the control source of magnetic tellurics.
Excellent. Listen, thank you very much for that. It gives me, actually, you get quite a few things out of that. First of all, there's a fair number of students. Second, there's a range of backgrounds of people who perhaps don't have a lot of information about electromagnetics, backgrounds in seismic and potential fields, but not so much in EM. We've got professors, we've got students. The other thing I was actually pleased about, and actually a little bit relieved, is how good everybody's English is. So I like this is kind of important, right? Because I'm going to be talking all day, and I will try to speak very slowly, and if there's, if I rattle on or something, you can try to stop me and slow me down. But I feel much more confident that I could hopefully communicate something to you today. So thanks very much for that. Can we dim the lights a little bit more in here? Or is I thought, since you've told me about yourself, I'll tell you just a little bit about me. I did my PhD many years ago. My supervisor was Bob Parker, and there were two people, Freeman Gilbert and George Backus. If you look in the historical papers about inverse problems, you will see these names. They studied the geophysical inverse problem. They really set up the framework for how it can be solved, and I was recipient of their mentorship. To give you a bit of a background on how things have progressed, in 1975, we were at a position that we could solve perhaps the 1D magnetotelluric and DC resistivity problem with maybe 50 variables. 1985, the workstation appeared, and we could solve 2D problems, the DC resistivity, IP, with perhaps 1,000 variables. 1995, we can start to solve the 3D problems, potential fields, gravity, magnetics, DC, and IP. By 2005, we were able to solve the 3D frequency and time domain EM problem with a few sources. There were two big things that happened. One is that there was the ability to take matrices and factor them to allow us to solve the problem using what are called direct solvers. That means that we can handle multiprocessors, and those multiprocessor machines became available in this time period. What that meant is by the time of now, 2015-17, we're actually able to solve the 3D frequency and time domain problems with many sources. And that is sort of the state where we are today. There's some factors that are important in addition to being able to solve these problems. And one is that you need to have good instrumentation and data. And what we're seeing today is that the new systems are providing a large amount of data with unprecedented quality. Here's big scale data over California for a water issue, magnetotelluric sites all over Australia, and offshore problems of hydrocarbon de-risking. These are all large amounts of data and high quality, and that allows you to do something with it. You need to have good data. The third thing that has transpired is that we now have many open source resources. So that allows people to share software, to collaborate, to test, to do interactive computing. And importantly, there's a lot of open source software that is becoming available. One I'll talk about, which has been developed from UBC and now participated by many others, is something called SIMPE. Most of the work that I'll show you today has been based upon. And then we have things like GitHub to allow us to communicate. The last thing is we also have many applications. Even around the world, geothermal came up quite a bit, as well as hydrocarbons and minerals. But here's places where electromagnetics could be applied, whether it's minerals, contaminants, water, geothermal, unexploded ordnance, hydrocarbons, slope stability, or geotechnical problems. And there's many more. So that's important. There's many different applications. So that means that we have the basic ingredients. We've got problems, we've got high quality data, we can invert those data sets, and we have web tools to communicate. So if we have all that, then the question is, okay, well, what are the roadblocks? Why are not people just using electromagnetics in every circumstance to solve problems? Well, here's some of the roadblocks. In general, the geoscientists, they really don't realize the role that electromagnetics can play in solving their problem. And then they don't understand the technique, right? The jargon is confusing, the terminology is confusing, right? So people are talking about, oh, well, the real part of the data, or the imaginary part of the data, or parent this or parent that. So it doesn't really, it's not intuitive. It's not like seismic where you can see waves going down and bouncing off of something and then coming back. So electromagnetics is complicated and it's unintuitive. So that's the problem. And then the other thing that's important is like, okay, what's the connection between my problem and the physical properties for electromagnetics? You need to understand what that is. And then finally, even if you do figure out that EM should be useful, then there's all these problems like, okay, what kind of survey should I use? Should I be in DC resistivity, frequency domain, time domain? Where's my sources? Are they in the air, on the ground, underneath? Just what do I expect for resolution? So those are all kind of practical problems that you have to, questions that you have to address. And then the other thing, which is also, I think, from a practitioner's viewpoint, if you have a problem, then you want to know, is there somebody else who had that same problem and was able to use electromagnetics successfully? Because if you did, then it'd give you some confidence that, yeah, maybe I could go ahead and do that too. So these are the roadblocks. And then the question is, okay, what are we going to try to do today? And this is basically what I'd like to do. I just want to get rid of that. So that by the end of the day, I hope that most of these things will no longer be any kind of a roadblock to people here, and that they'll have an idea about how we should go and use EM in solving our problems. So, why the disk? The disk, we feel this is the perfect time to do that. We sort of have a perfect storm because we've got problems, right? We've got high quality data, we can invert the data, and we've got web tools to communicate. So let's put it all together and do something. So it's a good idea, but we're missing one important ingredient. And what is that? What's the thing that's missing so far? Yourselves. We're missing these, bright young people. Most of you have got a lot of students here, young professional researchers. That's the missing ingredient. I have two people. One is Lindsay, who's sitting down here as a co-presenter for the DISC, and the other is Sagi Kang, who's another co-presenter with me. And it's people like these that really push the field forward and have the enthusiasm and the ideas and wherewithal to really get it. So with all of these things, we have a perfect storm. Yeah, let's try to make it useful. So the goals for the DISC, first of all, I'd like to inspire you. So to see a variety of potential applications and to illustrate the use, the use of geophysics through those case histories. I want to build a foundation. So if you have to understand the principles in order to apply. So many times people have misapplied EM just because they kind of forgot what some of the basic principles. And we're going to do some exploration and visualization through interactive apps. So we'll be talking more about them through the day. Widgets, small computing software programs that allow you to ask questions and to get some answers. And I'll talk to you about our open source resource called GeoSci. That has most of the technical material that we've talked about, we'll talk about in course, and a lot more. Then I want to set realistic expectations. So we're going to do that by looking at various surveys and seeing what they can provide. And lastly, and this is really important, and I think it's especially important in, well, Mexico, throughout South America, places where you may not have all of the advantages of, a really high technical university, or just all of the technical widgetry that exists. And that is that we're trying to develop an EM community so that it doesn't matter where you are, at which university around the world, you actually have a group of people, an EM community that you can work with, that you can ask questions with, that you can share with. And by doing that, promote your own education as well as solve problems that are really important. And working as a community, working as a group, is far more effective than always just being by yourself. And we want to capture case histories. We want to find out what people are working on here, and I'll talk more about that later. So what's our resource? There's GeoSci. You'll be confronted with a page that looks like this. Here's an image. How many people recognize this image on the left? Oh, that's pretty good. So there's more than a quarter. So this is a book that was published by the SCG. There's a very, very good chapter in there by Ward and Pullman that really outlines the basics of electromagnetics. So technically it has a lot of information, perhaps most of the things that you want. But it is difficult to really assimilate and understand what's going on. And that's the purpose of this resource here, which is basically to take a book like this and make it live. It's got background information, and it also has case histories. We're going to be going through many case histories today, and they're all going to be presented in what we call a 7-step framework. I think for people here, if you were to talk about your problem, that you would put that into this 7-step framework. Because the first step is to really articulate the question. What is the thing I really want to have answered? And what information do I know? Then the second is, okay, what physical properties are relevant to that? Then what survey should I use? What are my data? What processing am I going to apply to those data? What's my interpretation? And then finally, what's my synthesis? So we're kind of going to go around this loop. And one of the things that this does is help to categorize your problem, so that when you are speaking to someone about a problem and you put it into this 7-step framework, he can see, oh yeah, well you're here and you're having some problem going from the data to the data processing or something like that. But it just makes it greatly eases the communication and the understanding of what's going on. And the other thing is these resources are live, so they can be edited on GitHub. Traditionally, the disk course, as it goes out through SCG, one of the requirements is whoever presents it has to give a book. We decided that that was not a very useful, well, I mean, it's a useful thing, but we could do better by taking that book and making everything as an open source resource. And then that allows people to edit things, it allows people to contribute to things, as well as ourselves. So it's a growing piece of knowledge, and that is really the motivation. And why the apps? Well, I can show you this. So there's Maxwell's equations, there are 2 of them. And there's a lot of information in there, but it doesn't really resonate, you need to do something with them, and if you can somehow convert them into an image. So here's an example of just an electric dipole buried in a hole space, and you're able to see the fields and plot up what the responses would be, and to be able to change things like frequencies or conductivities. So they say once you go here, then you have something that you can interact with and learn from. So how do we achieve our goals? Well, we're first of all going to connect to relevant applications. And then we're going to select a type of survey, use the apps to explore and ask questions, and then show the success in a case system. So here's our agenda for today. What we're attempting to do here is something that I think is pretty unusual, and that is that we want to try in one day spectrum of electromagnetics. And the reason for doing that is that at the end of the day, when you're faced with an electromagnetic problem, you kind of have an idea of where you should be and what each of the techniques would be. So we're going to start off with the most fundamental, DC resistivity. Then we're going to do electromagnetics, just the fundamentals. Inductive sources, both frequency and time. Then we'll do grounded sources. Then we'll do natural sources. So here's where the MT comes in. Do the GPR, that's high frequencies. And then induce polarization and talk about the future. That's a lot of stuff. It's a very ambitious schedule. But still, there's a broad variety of backgrounds here. So we hope there's something that is of use for everybody. And for those people who are really expert in this, I'm not sure that I actually have too much more that I can tell Dieter, for instance. But the thing that I'd like to say is that even if you know a lot, then there's a quote here that comes about. It's a quote that I took a photograph of when I went to coffee on a Saturday morning. Every Saturday morning, my wife and I and another group of people meet at a coffee shop and we go for coffee. We've done this every Saturday morning at 9:30 for 23 years. Tell the same jokes, tell the same stories, but 23 years every Saturday, and there's always a quote. And this was the quote that was there that one morning. It said, "That's what learning is. You suddenly understand something that you have understood all of your life, but in a new way." And if you think about it, there's a lot that comes, there's a richness that's involved. Even if you think you understand something, if you learn something a little bit extra or a little bit differently, it enriches your thought process about that. So for those people who are expert, maybe that's the takeaway. The DISC is a two-day event. The first day is actually sponsored by the SEG. The second day, tomorrow, DISC Lab, is going to be sponsored by the Geophysical Inversion Society. And what we want to do there is that we want to talk to you, we want to capture the problems that you're working on, and we're going to ask you to give a short talk for those who are willing, just a few minutes about, okay, what is the problem that I'm working on? So we can capture that and share it on the web. We've been very successful in doing that as we've been going around the world. And at each place, on the second day, people would talk about, I've got this kind of problem, that kind of problem. And we put that onto the web, and that allows people anywhere to look at, oh, Mexico. Oh yeah, here's some of the problems that there really were concerned about. There were, a lot of stuff on geothermal energy, for instance. Or you go to India, or you go. We went to Europe, and there they just were not particularly interested in minerals or hydrocarbons, but they were really interested in pollution, unexploded ordnances, waste dump things, groundwater issues. So different countries have different focuses of what they're really interested in. So as we go around the world, we're capturing these. And we're hoping that tomorrow we can get people to participate. I'll talk more about that. And the other is that we're continually inviting people to interact and to contribute. So Lindsay set out how to connect up to a Slack channel. That's a way that we can get a community together. You can ask questions even for what's going on today. If you want to raise that or provide some insight. It's just a way of communicating that turns out to be very flexible. How many people have signed on to Slack? A couple. Okay. Perhaps by the end of tomorrow more. Yeah, and then contribute to GeoSci, both the case histories and the content, and maybe through software initiatives, through SIPA or other kinds of software that could be shared. So what I'd like to do now is give you a short introduction to electromagnetics, just a brief overview of where we're going, and then we'll talk about DC resistivity. Hope to do all of that before coffee break. So here's three problems. There's a minerals problem, unexploded ordnance problem, and a water problem. So you can imagine that there's all kinds of challenges that are associated with that, and we want to somehow either locate or characterize these. The essence of everything that we're going to do is with respect to physical properties. And what we have here is the one that we'll be focusing on most today, the electrical resistivity or conductivity. So resistivity tells you how difficult it is to pass current through something. So this is a scale. It's about 7 orders of magnitude. The resistivity is in a unit called ohm meters. Very small resistivities connected with massive sulfides or granites. So it's easy to pass the current through. Very large resistivities are, let's say, metamorphic rocks, dolomites, limestone, permafrost. Those do not pass electricity very easily. Most of the things that we're concerned about fall in this mid-zone. Hydrocarbons are sort of in here at 100 meters. So these are the resistivities for different units, and you'll see that each, a particular unit doesn't have an exact resistivity. It can span over many orders of magnitude. The reciprocal of resistivity is conductivity. So it tells how easy it is. And so the numbers are in here, and they will be either in, their unit is Siemens per meter or sometimes millisiemens per meter. As geophysicists in electromagnetics, we often flip back and forth. We'll talk about resistivity, the resistivity of the rock, or we'll talk about the conductivity of the rock. And sometimes we just almost even do it in the same sentence, which just takes a bit of getting used to. But there's no real way around that. And I'll be today talking about either resistivities and ohm meters or conductivities. The second physical property is electrical permittivity. And if we take the ratio of electrical permittivity to that in free space, we get the relative permittivity. And sometimes it's referred to as dielectric constant. This is something that's especially important in ground-penetrating radar or high-frequency EM. And the important thing here is that air has a value of 1, fresh water has a value of 80, and it doesn't matter whether it's fresh or salty. Everything else is in between. The third physical property is magnetic permeability, or effectively magnetic susceptibility. So this tells how easy it is for a rock to become magnetized in the presence of an external field. And again, this can vary by many orders of magnitude. The most magnetic material is magnetite, sitting right up here. So this is dimensionless unit. And then you've got other rocks here, gabbros, metasediments, that have a range of magnetic susceptibility. The general geophysical survey actually looks like this. Any geophysical survey can be put in this form. We've got a source that puts energy into the ground. There's physical properties, conductivity, permeability, and that energy is some of it's propagated back out, and we measure it as data. So your source, physical properties, the data. This is a non-mathematical course, but we still need to look at Maxwell's equations, and this is what Maxwell's equations look like. They can be written in time domain or the frequency domain. And there's various laws that go through it. There was Faraday's law, that was this one. And basically that says that if you've got a time-varying magnetic field, you're going to get an electric field. There's Ampere's law that says, well, if I've got a current, I'm going to get a magnetic field. And then we've got these constitutive relationships down here. The one that we'll use mostly today is this one, that the current density is related to the product of the conductivity and the electric field. So this is known as Ohm's law. So these are the equations written in time, these are the equations written in frequency. The relationship between them is just very transparent. The thing is that every problem that we're going to deal with today, and every problem actually involved in electromagnetics, whether it's in transmission of your light, generation of electricity, transmission of your cell phone, everything is based on these equations. These equations are actually fundamental free, and just the difference is what are the sources and what are the boundaries. So let's just talk a little bit about the surveys. So here, first of all, there's the sources. Well, we can have multiple different kinds of sources. We could imagine a grounded source where we take wire, put a generator up to it. So that's a grounded source. We could have an inductive source. So here, nothing is touching the ground. It's just a loop of wire. So that's the source. They can be inductive or grounded. I'll use those terms today. And then, what sort of a signal are we going to put through? Right? We could put in a harmonic signal that looks like this, so it's just a single frequency, or we can put in a transient, a time domain signal that has some character to it. And then the third thing that for the sources is where's the location? Is it in the air? Is it on the ground, or should we put it inside? So there's choices. We have a EM source, but there's a lot of choices about the details. Now there's the data. Okay, so if I'm going to measure something, well, what could I measure? I could measure, say, a magnetic field, and 3 components. I could measure electric fields. Okay, so those could be frequency, electric field or magnetic field, either in frequency or time. And then if it's in frequency, which frequencies should I measure? Is it really low period or really high frequencies? If I'm in time, I might have a decay curve. Which times do I want to measure? And again, for my components, could be X, Y, or Z, and then location in the air, on the ground, and forth. So again, my purpose of showing is that there's a lot of potential here for opportunities of different kinds of data. If we look back at the 3 problems that we talked about, one of the things that we notice is that the electrical conductivity is diagnostic. The water, well, so the minerals, for instance, there's a lot of minerals are highly conducting or very resistant background. Unexploded ordnance, these are steel, so they're conductors. Water, conductivity is a very important factor for delineating water. So we could imagine that our surveys are considering some kind of source. We're just looking for electrical conductivity at this point, and we're going to try to connect that with the data. So with that, then I'm going to now go to DC resistivity. This is one of the oldest techniques and probably most familiar to people, but I'm going to present it in a bit of a different way, where the emphasis is going to be actually on understanding how the DC survey is connected with electrical charges. How many people here have done a DC resistivity survey? Oh, sweet. Okay. That's like about close to 80%. That's good. We're going to go through it again. And here we are. For this, it's a little bit easier just to refer to resistivity. So I'm going to try to keep everything as resistivity, which is 1 over the conductivity. So here's our problem. Put energy in and get some data back, and we'll try to find out what the resistivity is of the Earth. What's our motivation for this? Well, mineral exploration, groundwater, oil, gas, groundwater, this is water flowing into a mine, and geotechnical problems, and a whole host of others. DC resistivity is just one of the basic workhorses for a whole variety of problems. The electrical resistivity, or conductivity, we had talked about with this previous image here. I think there's a couple of important things. Is first of all, resistivity varies over many orders of magnitude. Secondly, it depends upon many factors. So here's a rock, there's a penny, there's scale, and you can notice quite a few different things. It's got a different texture here. There's actually something different coming in here than there is on these sides here. So the resistivity of this rock is going to depend upon, first of all, what type of rock it is, whether it's a sedimentary rock or metamorphic rock. And then its porosity, there's a whole bunch of holes in here, and how those pores are connected, and then what the fluid is inside, how much fluid is there, and also what the metallic nature of the solid matrix is, how many metals there are. So you kind of get the idea that, even if somebody tells you the resistivity of a rock, that there's actually a lot of things that are going to go into that are going to impact upon where that number comes from. So I want to outline the basic experiment. I'm going to look at, importantly, the aspects of currents and charges, and I'm going to take you through things that are important, like sensitivity, and talk a little bit about survey design. So here's the basic experiment. So in this particular case, it resembles a mineral deposit. There's a central core here that is very conductive of resistivity. There's a resistive top or Gaussian here. There's a background resistivity here. That's the host material. There's an overburden. So the overburden is a bit conductive. This region is about 400 ohm meters, and this is much more conductive. Okay, so that's, you're trying to look for that. The basic geophysical or DC survey is as follows. We take a generator, hook it up to 2 current probes, and we're going to put electrical current in, and the current's going to go from the positive electrode to the negative, and it's preferentially going to flow through the conductors. An important aspect is that there's going to be charges that are going to be built up on the outside of this body, wherever the conductivity changes. And those charges are going to give rise to electric potentials that could be measured up at the surface. And to make that measurement, we're going to put in 2 probes with a voltmeter and measure that voltage. See, so that's the basic experiment that we're going to do. So we're going to take you through that, and also to try to understand, okay, how do we get the resistivity of the Earth out of that? So let's go back to Maxwell's equations, and we're in steady state. That's why it says DC, direct current. Nothing is changing in time, so that everything that has time dependence here goes to 0. So the equation's reduced down to something that looks like this. So we can get that the electric field is the gradient of the potential. We have Ohm's law. Put it together, we get this equation here, which is probably one of the most important and famous equations in, well, certainly geophysical electromagnetics. This is, and this equation is also used in groundwater flow. It's used in medicine. So you'll see this equation everywhere. Here we're using it for DC resistivity. If I take a uniform space, so now imagine just I've got a half space, I plunk a current into that ground. Then there's actually a solution for what the electric potential is away from this, from the current, that falls as this kind of character. So the voltage falls as 1 upon R and depends upon the resistivity. So we can use that in the following manner. So suppose I put a current into the ground. That what would you expect is happening? I mean, there's no preferential direction, so the current lines are just going to generate out. And the electric potential is going to be infinite right at the current electrode, and then fall off. Now the interesting thing about this is that if I was able to measure the potential at any place, let's suppose here, that I could actually recover what the resistivity is. I take my analytic equation, just rearrange it so that I've got rho on this side, and now I can plug in everything. I measure the voltage, I know the distance, and I know the current, and I plug that number in, and I get that the resistivity is 500 ohm meters. So that's exactly what this block was, and I can get it out from a single measurement. So it could be here, I could take one out here, doesn't matter. So that's really kind of interesting, right? Because you do something and you measure one number, and actually you can kind of convert that number to something that you're really interested in. Okay, quite do that experiment. In every experiment that we do, we actually need to have 2 electrodes for the currents. I'm hooking it up to positive and negative. And that's what happens here. So now if I put a positive current in here and a negative current here, you can see how the current lines are now flowing. And the electric potential that comes from that looks something like this. It's got positive and a negative. Because everything is linear and use superposition, I could actually calculate what my electric potential difference would be between any 2 other points. So here's the general experiment. For a DC survey, I'm always going to have 2 electrodes for the current. A is going to be positive, B negative. And then for my voltmeter, for my potential meter, I also have a positive and a negative, and I'm going to hook it up like that. And all of these R's with subscripts underneath just indicate distances between the various electrodes. So I can put all that, and I get that my measured potential should be equal to something like this. Again, rho times I. And that's just a geometric factor. And if I rearrange that, now I can write an equation like this, which means that if I take any 2 potentials, so I make a potential difference between any 2 points, I put that in here, and I get out resistivity. So again, I do that here, I get 500 ohm meters. Okay, perfect. What's going to happen now if I start to change the Earth a bit? And let's suppose I put a conductive layer. Let's suppose I have a thin conductive layer at the surface. What do you think is going to happen to the currents? Anybody? Yes?
The current will prefer to go through that layer.
So the current will prefer to go through the layer, yes. So now if we put a 100 ohm meter layer up here, then now the currents sort of preferentially go through here, and I measure a different potential difference. If I take that value and plug it into this formula, now my apparent resistivity is 226. So it's not 100, which is equal to that. It's not 500, which is equal to that. It's equal to some combination of them, which is, I think, perhaps intuitive that you're sort of sampling something of the whole region, and you end up with a mixed number. So we have an app to allow you to work with that. So you can play around, you can have different layer thicknesses and resistivities, and get a sense for what the apparent resistivity would be for different configurations. And you're free to use that. We'll talk more about how to actually use those apps and load them a bit later. But these are great because they allow you to ask questions and to gain insight into what's going on. There's a couple of things that are important here. There's has to do with the concept of sounding and which arrays that you're going to use. Here's our general core electrode array. Different configurations of the electrodes have different names. So this is called a Wenner array, and it's got currents that are up like this and potentials in here, with all of these guys being the same distance. Or you can have a Schlumberger array, which is basically the same as this, except that the voltages are different. So it's just the configuration of the electrodes that give rise to different names. The data that you're going to obtain, and we're going to do a sounding, and by a sounding, I mean I'm going to stand in one place, and I'm going to start with a small array and then just gradually make it bigger and bigger. And the idea is that we're going to do deeper. We're going to have a data which is our apparent resistivity as some function of the length of what our array is. So let's just take a look at that. So first of all, let's suppose that we've got the same situation as before, but now our current electrodes are just really close. There's only 5 meters different between them. And now, because everything is close and the currents are kind of going, inside this top layer, and so what we see is an apparent resistivity of 100 ohm, just a little over 100 ohm meters. So it's barely not influenced by this at all. And on our graph up here, our data graph, then we'd be sort of at this particular. If we make the sounding array a little bit bigger, now you can see there's more currents penetrating in here. Our apparent resistivity is now 135 ohm meters, so it's increasing. And more, it's now 240 ohm meters. So you can see what is happening. The farther away my electrodes are for the current, the more current that's going underneath the ground, and the larger the apparent resistivity is. There's a couple of things that are important here. The idea with the sounding is I'm just going to progressively increase the length, and I'm just going to see to greater depth. Another thing that is important is that to really get up onto this top part of the curve here where it's 500 ohm meters, just that I need to have an array that's very long. So you need to have large length scales on the array to CT. That'll become more important later throughout. The data curve that we saw here is that. It's just a data curve. This is apparent resistivity, and this is some kind of length. In order to do something, or to gain geologic information, we need to convert this to true resistivity and depth. So the way to do that is to what we call invert the data. So the idea there is that we're going to take our measurements, here's your data, and we're going to put them into a box here. We're going to process them and give rise to something that's got true depth and resistivity. Now, it's kind of interesting. Most of my life I've spent on looking on this box here on the inverse problem. That's most of my research. We're not going to do any of that today because that would just take us off onto a different tangent. So basically what we're going to do is show you many inversion results, but they're all going to be obtained more or less with the same kind of general technique. And that is that in 1D, for instance, we start off with a number of layers of different resistivities, but unknown. And then we adjust those values so that we fit the data and have something that's geological. We'll do that in 2D, in which case now the cells are cylinders, and we're doing it in 3D where things are just cubed. So it's not going to matter. Everything is kind of hit by the same formalism, and the idea is that by the time we take the data, put in some background knowledge about what we're looking for, we can invert that to get a physical property model as a function of depth or XYZ. So if we did that in this case here, the resistivity model that we get out, the true one may look like this block, and the recovered one through the inversion, would have something that was similar. In this case, it was a smooth inversion, so it kind of smears out that boundary, but you get the right resistivity at the shallow depths, and you get the right resistivity at the large depths. So now you've converted it to some useful. I want to go back now to this DC resistivity problem for a confined body. So the idea here is that I showed you we had current that was going through like this, and I said there's charges that are built up. Okay, so where does that come from? Where do the charges come from? That's what this slide is supposed to illustrate. So if we look here, because we've got a continual current that's going through here. So whatever current exists on here is also going to be going up in there. So the current densities on both sides are the same. That means that if 1 is on this side and 2 is on this side, so this is the currents are the same. But remember Ohm's law. Ohm's law said that J is equal to sigma E. So sigma 1 E1 must be equal to sigma 2 E2. The problem, well, the challenge here is that sigma 1 is not equal to sigma 2. And that means that E1 cannot be equal to E2. So that means the electric field has to change. The electric field is going to change discontinuously. And what's the only way in which we can get an electric field to change? Is to introduce some kind of charge. So when you were in first year physics, you calculated what the electric field would be from a sheet of charge. Undoubtedly you did that. And here it is. So if we have a positive charge on this boundary, then that gives rise to an electric field that points outward in this direction and outward in that direction. So that means the electric field is discontinuous. And that there's a charge buildup and, that is going on. And once we have those charges, then we can compute whatever electric field that we want to compute at the surface through Coulomb's law. Okay? So it's an important point because we're going to see charges a lot today. And they form a fundamental basis of everything we do. And the idea here is that you can see this. We've got a current that goes through. Current's continuous. Current is equal to sigma times E. Sigma changes. that means the electric field must be discontinuous. The only way that can happen is if there's a charge. So let's look. So here's some examples. So now let's put up a current. Now we're going to put in a little sphere cylinder in here, and the current is going to come in, and you can see that how the current lines are changing. They're kind of being sucked in, which is what you'd expect. If it's a conductor, then currents are going to flow in. If we look at the difference between what we call the primary currents are without that, and these total currents, we subtract them and we end up with these as secondary currents. So secondary currents are the difference between what you see and what the currents would be without the object. And you can see, looking here, you can see they're kind of dipolar in nature. So these are the secondary currents that exist in the ground. The quantity of importance here are the charges on that sphere. So as the current goes in, there's a negative charge that's built up on this side. Current comes out, there's a positive charge. Those charges give rise to secondary potentials that are here. This is our signal. This is the guy that we're ultimately going to try to observe, and we're going to be measuring something at the surface. If we think about trying to, what we'd see if we did a DC measurement over that, this is going to be a gradient array. I'm going to put my currents, one over here and one over here. Actually, I did that here. So I'm just going to leave my currents the same, and now I'm going to try to measure what the apparent resistivity would be at various places along here. So if I do that, my potential curve looks like this. And if I measure a voltage, let's say right in here, I get 430 ohm meters. So that's good. It's less than 500. So that was the background. Now I've got this sphere in there. Do something, I measure it, I get 430. So, you know, the apparent resistivity curve would be dipping a little bit, maybe indicative that I've got if I go out to the sides, so if I'm sitting out here and I measure the potential, I actually measure a potential, which when I put in calculated apparent resistivity, is 502. So I measure a resistivity that's actually larger than the background, and there's a kind of a question of how that can occur. So we're going to explore that a bit later. But at this point, what we see is that if we had a fixed current out here and we measured the potentials as we go across and converted them to resistivities, we'd have a high value here, 502, a low value, and then another high value. This, the existence of something that varies laterally means that you also want to do what's called a profiling, or moving your whole system laterally. The concept here that's important is it's related to what I had before. So if I have a very small array, so let's suppose I've got something that looks like this. So here's my current electrode, and here's my potential electrodes. And now, if I'm going to move this across, okay, then I'm only sampling what's actually very close to my electrodes. So I'm not even getting down to, you know, Lindsay or where Dieter is sitting back there. Just my depth of penetration is too shallow. And as I'm walking across here, so here's my cylinder, it's 1 ohm meter. I'm moving across here, but my whole system is so short that really I'm just going to be measuring 500 ohm meters, just what's happening right beneath me. If I take that same survey and I just expand it, So I make it bigger between each of the electrodes. Now I'm going to see deeper. And now if I profile that as I come through, then no problem seeing Dieter or anybody else in that group, right? So it's high here, it's very low here to 300 ohms. So the conductive sphere, which is sitting down here, is really readily identified. If we put these things together, the idea of a sounding, which just preferentially looks deeper, and profiling, which moves across laterally, then we have a combination of a survey that looks in 2 dimensions. So we're going to both expand and translate. And to do that, there's a whole bunch of surveys, geometries that you could use. There's the Leonard-Schlemmer that I just talked about. There's a gradient where we put up current electrodes here, and then we just measure in here. This is actually done a lot for mineral exploration as a quick kind of reconnaissance tool. And then there's these guys here, pole, dipole, dipole, dipole. You'll see these a lot. And basically, in order to get a pole, we're always with 4 electrode systems. But if I take one of these electrodes and I ran it way out this way, then I would actually, it'd be like there's just a current pole and then a dipole. And so that's referred to as a pole dipole. And if I ran the other electrode up, I could have basically a pole-pole. So you're always dealing with 4 electrodes, but sometimes if you take one electrode, run it 2 kilometers out in a particular direction, then you can refer to it as a pole. We have to plot the data. If you have 2-dimensional data, you can actually plot it in a plane. And this is generally referred to as a pseudo-section, and I'll show you how that works. So here we've got a so here we've got a 2-electrode, 4-electrode array of dipole, right? And I calculate a voltage, and I'm going to have an apparent resistivity that's associated with it. So, okay, I just want to plot this stuff on a piece of paper. So what do? I'm just going to make 2 planes. I'm going to take a line, draw that 45 degrees, and then I'm going to put that point. If I move this apart, then these lines will intersect at greater depth. Move it apart, it's there. So what we see, you're going to have a plotting plane in which this is somehow related to depth, and at the point is going to be plotting the apparent resistivity. So I can show you how that fits together. So what we're looking at here now is progressively moving the current electrode, and each time we move the current, the potential electrode continues to move. So we build up all these apparent resistivities, and then we contour them in. So what that did was to generate, I'll just do that once more, because even though these things have been around for a long time, it's interesting as to some people still get confused. Because it's a way of plotting the data that is, so this current electrode is progressively moving along here. Each time he moves, then the potential electrode comes out here, and they're all plotting these points and then contour. Just to show you some examples of the data plotting. Here is a conductive block in a uniform half space. And that's what we're going to try to find. So we're going to do a DC resistivity experiment over top and plot the data. The data plots up as a pseudo-section. So that's our pseudo-section. And the question is, okay, what information could I get from that? And should I interpret? This depth here is a pseudo depth, is just related to the end spacing of the system. And if you look at that, you go, oh, maybe that's not so bad. Especially, have a block, might have some wings on it. Maybe I should drill in here. And if you went ahead and did that, you'd have been successful. This situation is a bit more representative. We've got the block, but we also have a lot of this kind of geologic noise that's sitting there. And what does that do to the pseudosection? So here's now my data. Well, that's a picture of the data. You cannot get any information about this block at all. So that's one example. The second example looks like this. So we've got two conductors in here. And go ahead and do the DC resistivity survey. Here's my pseudosection. Here's my plot of my data. It's really tempting to drill on a high value. This is what happens way too often. Just drill on this high value. But if you did that, you'd be drilling right through here, you'd miss both of these conductive targets. So that's a problem. And the important point I want to make here is never make a geologic interpretation on the basis of a plotting of the data in a pseudosection plot. So what do we need to do? We need to invert the data. So we're going to do the same thing. We've got our data, and we're going to invert it and see what we get. In this case, it's going to be a two-dimensional model. So we're going to take an Earth and make a whole bunch of cylinders in it and evaluate those. So now if we go ahead and we look at this buried prism. So here is the resistivity. Here's our data, it's our pseudosection. If we invert these data here, this is what we recover. So this is actually pretty good, right? We've got a conductor block sitting here. It's at the same space as them, so it's properly centered. That's at about the right depth. It's smooth. It's not sharp, but that's because of the inversion process. We've asked for a smooth inversion result, and we fit the data. If we look at this one, remember the one that was so bunged up? So we've got a pseudosection that's uninterpretable. But if we invert it, we not only recover the block, but we've actually recovered this stuff up here. So maybe that is just geologic noise, but maybe it is something that is of interest, and we've been able to extract that. So that's the power of inversion, and here's our JIT model. Here was these two conductors. Here was the pseudosection. We invert, get this. And again, they're in about the right location. They don't extend as deep because the survey just didn't have that kind of information. But you do have high quality information about the existence and location of the two conductors. Well, the world is 3D. And there's a lot of things that are important here for our target. Okay, what's the size? What's the shape? What's the depth? What's the background connectivity? How variable is it? If you're, here's your host, right? And maybe you got some topography. Things are complicated. So now there's questions like, okay, where do I put my current electrodes? Should I do a 2D acquisition, or do I need to do 3? Where should I make measurements? What's the effect of topography? These are all questions of survey design. They're questions that you'll ask yourself each time you're confronted with something. But there's a crucial element in here, which is called sensitivity. So I'm not sure, from the point of view of survey design, and if you're looking for something, if I talk to you about sensitivity, anybody willing to share a definition? What would I mean by sensitivity? Graduate students in the back. Sensitivity, yes.
How much will ever change the properties
Perfect. So I want to decide if taking a particular measurement is going to do me any good, right? And in order to kind of quantify that, I want to try something, some geometric layout, and then I'm going to change a parameter in here. Maybe it's the resistivity of this block, maybe it's a boundary, whatever. So I'm going to change that, and then I want to find out if I change that a bit, how much do I change the data? And that ratio, the change in the data divided by the change in the property, gives me something called the sensitivity. If that number is large, then it's good, right? Because now I know that my data are highly sensitive to this parameter, which means that in the inverse problem, I should be able to get that parameter back up. So that's good. That's the essence of what you want to do. Most times when people talk about sensitivity, they kind of lump all of that stuff together. I don't want to do that because it's much more beneficial to actually take this concept of sensitivity and break it up into two parts. The first part is you need to excite the target. You need somehow to have a transmitter, a source that excites the target. And then the second has to do with, okay, which data do I want to have? That means that you want to be closed or in a particular orientation. So it helps very much to break those two things down when you're trying to think. Let's just take a look at that. So let's go back to this conductive sphere that we have. Here's our total current, here's our secondary currents, our charges, and you can see that in this particular case, we've ignited this body. And look at the charges on here. Lots of big charges, positives and negatives. So this configuration, having a current here, is really good for exciting that target. So that's good. And there's our secondary potentials. So what about the measurements? Well, the measurements in some cases, like in this, are kind of almost intuitive, right? Because we're going to measure the potentials that are associated with these charges so that basically we want to be as close as possible, which if we're confined to the surface, we're up here. But if we had a borehole, then it'd be really nice to put one end of our potential measurement down here. So going along here, we can see that we'd be sensitive to these different charges, and these would be good measurements to take. And if we convert those to apparent resistivities, then we get out something that we have. The thing that we haven't yet talked about is something that is called coupling. So let's suppose that we have a plate. Now I can take a plate and put it different orientations. So the plate could be in this direction, or it could be in that direction. And then there's a question about how well do we excite the target? Okay. So if I put the plate here, and I looked at my current, and you can see that, okay, I've got some deflections that are coming in here. So things are changing. We have to look at the charges to see how effective we are. If I lay the plate horizontally, conducting plate, I can see that I've really changed how things are coupled. So by looking at the currents, you get an idea of how the orientation of the plate is really altering, making a difference from what you had prior to that. The other thing that's really important is the conductivity. So the plate that we just talked about could be a conductive plate or could be a resistive plate. So what does that do from the point of view of excitation and excitation of the target? Well, look at this. If we have a conductive plate, so in that case, you can see that there's currents that are kind of being channeled in. If here's the charges, there's negative charges here, positive charges here. So you're doing okay. I mean, you are in some sense igniting But look what happens if you change it into a resistor. So now I make this a resistive plate. Now the currents have to go around it. So instead of going through, you have to go around. So there's large distortions in the current. And in order to do that, you need to have lots of charges that are built up here. So here's my strength of the charges. They're like a factor of 5 more than this. So if you're looking for a resistive plate versus a conductive plate, there's different strengths that you're going to see. The other thing that's noticeable here, when you have a conductive plate, notice the negative charges on this side, positive here. If you have a resistive plate, it flips. So you got positives here, negatives here. So the kind of summary points that I want to make here with respect to this is that you need to excite the target. Right? So you need to drive currents into that target, and you need good coupling. So that depends on the orientation that you've got. For measuring the data, you want to be in proximity to it, and you need to have the proper electrode orientation and length. So remember, you're going to measure voltage that depends upon, not only the electric field, but the distance between the probes. And yeah, then the other is that you're doing this in background, so that background is going to be important. So if we come back now to questions of survey design, then the first is, okay, what's your objective? Do you have a layered earth? So if it's 1D, you're good. A sounding, that's good to go, right? You just stand in one place and you just progressively move, see deeper, you're okay. If it's 2D, then that is also still okay. Because now you could do a survey, you do it perpendicular to that geologic strike, and acquire both kind of sounding and profiling data inverted. If it's 3D, well, then you really need to have 3D coverage. You need to have currents going into an object from many different directions and to measure a lot of different electric fields. The other thing that you need to worry about is what's the background conductivity. I'm going to come back to that a little bit more later. And then noise sources. What are the noise sources? Fences, power lines. So those are basic questions. Many of them are challenging to address without appealing to numerics. And basically, this is the general flow. It doesn't matter what problem you're working with, you kind of end up doing this. So the idea is the following. You've got a background geology, and now you think, oh, maybe there's a mineral deposit, or maybe there's something else in here. So I want to see if I can see that, and see if my particular survey is going to be sensitive to that. And this is the steps. So you first of all have to define your geologic model, and then you assign physical properties to that. So the first thing might just be, structural geology, or somehow making a 3D geologic model. And then for each unit in that geologic model, you assign a physical property. Then you select a survey. Let's say you decide to put currents in one particular location, or you do something else. And then you simulate with and without your target being in. So let's suppose you've got a background geology, you simulate the data, you get the blue curve. You put your target in with a particular orientation, calculate the same curve, or same data, and you end up with these as data. So now you know that there's a difference between with and without target. We'll call that delta V. So that's the difference with and without the target. If the hypothesized survey is going to be good, that difference needs to be greater than some floor value, because you've got some background noise. And generally, it also needs to have a percentage, be significant in a percentage manner from whatever your primary is. And a lot of time, actually, this is a really important point when you come to do inversion. because one of the things with inversion is you need to assign uncertainties in a data. And for many data sets, DC resistivity in particular, a percentage error is appropriate, as well as maybe a floor. And the percentage error assignment is due to the fact that there's just this large dynamic change in the values of the data. And even if you misplace an electrode location by a meter or something, you can have a really large change in the potentials. And so a percentage error in the floor is often useful. So that's kind of the same criteria that we use here. So now what I'd like to do is to show you an example. This is a case history. It's a mineral deposit. It's Mount Isa. Sometimes it's called the Cluny deposit. So I'm not sure if you can see that. That's a map of Australia. There's the area that we're interested in is up in the northern part. And we're going to step through, I'm going to present this case history in a 7-step framework. So here's the setup. You're starting to set up properties, survey, data, processing, interpretation, and synthesis. I'm going to go through each of these. So first of all, the setup. What's the problem? Well, it's a mineralization problem. Here's a geologic model. At this point, it doesn't really much matter what these colors are. These are all different geologic units. A couple of things that are important is that there's something called a breakaway shale. It's this guy in here. He'll turn out to be quite conductive. We're actually looking for something called a Mount Nova horizon. That's a mineralized zone. That's kind of in its purple part here. And then there's a whole bunch of other volcanics that are in here. So we've got a variety of shales, siltstones, volcanics, and we're trying to find this mineralized one. From our point of view, at this point, our question is as follows. Can a conductive unit, which could be a potential target within the siltstones, be identified with DC data? So basically, we're trying to find a conductive target. To be more explicit, we need to look at the physical properties. So the physical properties are given in this table here. And of particular importance is the sort of the Mount Nova horizon, which has a high conductivity. The volcanics have a very low conductivity. Siltstones have a moderate conductivity. And so we're expecting that the thing that we're looking for, this Mount Nova horizon, has a high conductivity. It's buried in the siltstones. So we should be able to see it as something that's a bit higher conductivity than that background. The fly in the ointment here, or the problem, is that there's another unit, it's called this breakaway shale, that has a very high conductivity. Okay, so from a geologic perspective, we've got a mineralized body that's sort of surrounded by something that is less conductive. There's some really resistive volcanics out there, but there's also another unit that has very high conductivity. So let's see what we can do. The survey was done in the following manner. The geology is running more or less north-south. So because of that, you feel like, okay, maybe I could collect data in a 2D format. So just just do a number of different lines in them. So that's what was done. So there's 10 lines of data that are acquired. And each of them then gives rise to its own data map or pseudosection. Right? So along here, we would have a pseudosection that's like this. So the data are going to be acquired in a pole-dipole sense. Right? So we take one current electrode, run it way up here, and we go ahead and measure those. So when we do that, we see that we've got 10 lines of data, so we've got 10 10 pseudosections. And, you know, what geology, if you look at that and you ask, okay, well, what do I see geologically? It's not clear. There is something conductive here, right? So that the red is conductive, blue is resistive or very low conductivity. So that's 10 maps of data. Not a good geologic representation. I also talked about excitation, right? So if I put in a current from one direction, okay, I'm going to excite the body one way. If I put a current in from another direction, I'm going to have a different excitation. This was a dipole-pole experiment. So now I take my current and I run it way up to that side, so I've got my current on the left. Notice the difference that you see in the data maps. So there is definitely something conductive in here. So our goal is to make some geologic sense of that. So what do we do? Now we're going to take a cube, big volume of the Earth, and now we're going to divide it into a whole bunch of small cells, okay, so that we end up with, I think in this case, it was about 500,000 cells, at least on the first one. So 500,000 cells, and we don't know the value of each of them, so we're going to adjust them through the inverse process so that we fit these 10 pseudosections and the previous 10 sections. Now what I'm going to show you here, this is the result of that inversion. So these are just the values of all the cells. Red is really conductive, blue is resistive. And the animation I'm going to show you is going to be slicing through this guy from front to back, and then we'll come back again. And then we'll slice it from top to bottom so that we have planned sections. And then it's going to rotate around, but as it rotates around, the isosurface value is going to get progressively higher, so that at the end of the day, the only thing that we're going to see is the most conductive unit. So you see that big conductor on the right. Now we're slicing back. Now we slice top to bottom, that big, long, linear conductor. Now we rotate. And we end with this. So that's the final image. That is the most conductive unit there. You see there's a couple of other guys. And we plot it back in the color scale. It looks like this. So what have we done here? We've taken 20 pseudosections of data. We've put them into an inverse program. We've got out a 3D conductivity model. And we now have something here that looks a lot more geologic. So how did we actually do it? Well, it turns out we actually did pretty well. We got this big unit in here. Remember I said that the highest conductivity was this breakaway shale. So this is clearly that unit there. There's some volcanics, these really resistive regions on the outside. Those are volcanics. And then there's this kind of moderate resistivity regions in here. These are basically the siltstones. And there's a region in here that has got moderately high conductivity in the siltstones. So it turns out that this image is actually has provided a lot of geologic information. There is some hint that this is the unit that we might be after. But at this point, the DC resistivity has not been totally diagnostic. I mean, there's not enough information in there to go and have a fair bit of confidence that this is going to be a mineralized zone. And we're going to come back to this later this afternoon. In fact, it's going to be the very closing things that we do. Because it turns out that electrical conductivity is not, as I said, the thing that you want to do. These rocks are also chargeable. So there's an IP response that's associated with it. And it's the rocks that are both highly conductive and chargeable that constitute the mineralized zone. So we can't come back to that particular problem, but we'll do that at the end of the day, and we'll see the final interpretation. Oh, yeah. So we have, as we've been traveling around the world, each place that we go to, there's other case histories that are really important, and so we've been kind of emphasizing them. But we've included all of those case histories in the slides that you've got. And we're not going to have time to go through all of these case histories. I'm just going to tell you basically what this guy does. And then the full case history is there. I mean, it is the kind of thing that if there was one of the case histories that we don't discuss today, but people are interested, we could do that tomorrow. We have enough flexibility to do that. But today, because I'm trying to get through all of this material, I can't really get across to it. But this was kind of an interesting example using self-potentials. Actually, use self-potentials and DC resistivity. But the idea here, what you're looking at is an embankment dam. It's in France. And there's sort of water on this side. And then there's, here's the sort of pasture land, and there's a ditch in here. So here's the land side of the dam. And you're looking to try to see if you can find out where the water is coming from. So there actually is a small leakage of water through this dam. And the idea is to use self-potential measurements to try to find out where that water is, and actually even to convert it into the flow rate. So to find out like how many liters per second might actually be coming through. So it's a combination of using lab work as well as field surveys to try to put all of that information together and to do monitoring of dams. Now, I'm not sure where monitoring of dams fits into a Mexican. If you go to Korea, for instance, we had a scientist from Korea visiting UBC, and he said it's a very much concern there because there's like 17,000 dams that they have. They're not all huge, but they could be 20 meters or 50 meters or 100 meters across. And a lot of these are just earth-filled dams. They are, some of them are starting to leak, and so we need to monitor them. And techniques for monitoring could include DC resistivity, they could include self-potentials, and could use EM techniques in general. So it's a problem, and when we're in Germany and in Europe, also there is problems with dams. And tailings dams, it's another type of dam that is potential. So dam integrity and dam safety is, I think, an issue that one sees in a lot of places. So there's case history there about that. Just a second. And the thing that I want to do now before, just 5 minutes before we have break for coffee, I mentioned a couple of times effective background resistivity. I want to explore that just a little bit more. So here's the example we did so well at, right? So 500 meters, here's this guy here, put in a current, they get deflected, right? So no problem. The question now is, like, what happens if I take this and I put a resistive layer in here? Okay, so let's suppose I take a thin layer, very high resistivity, and I put it in just above the sphere. What's going to happen? All our graduate students in the back row, what happens? Anybody? Oh, come on.
Conductive or resistive?
Resistive. Okay, what's going to happen?
Sensitivity to your target.
Yeah, what happens in currents? Pardon me? Yeah.
I guess current about resistivity.
That's right. So the current is going to have a very difficult time getting through something that's really resistive, right? So that's exactly what's going to happen. So now I put this layer in here, okay? And all my currents go up here. So I've got this conductive sphere in there. I come along, I got an apparent resistivity of 1600 ohm meters. I was looking for something that was less than 500. So it's now just that resistive layer in there means that you're right. I'm shielded. I don't see. There's not currents that are coming through here. All the currents are coming up here, and I just have this very high apparent resistance. And to show you that is really only the effect of this resistive layer, I take that cylinder and I remove it, and I get the same apparent resistivity. So this is a really, really important point for the DC resistivity. I can take a very thin layer, it can be very thin, and as long as it's resistive enough, that can completely prevent any kind of penetration. Okay? So that is a very, very big problem for DC resistivity soundings in places where you've got conductivity. Or you can imagine even if you had a big crack in the rock, right? There's not going to be any currents that are going to go through. Okay, what happens if I have a conductive layer? Pardon me? Penetrate?
When it's very conductive or very resistive.
Right, okay. So if it's very conductive, now this is what I'm going to have. So now everything just gets channeled into this conductor. So I don't get any currents up in here, I don't get any currents down below, and everything it goes down into the conductor, short circuits across and back up. And now my apparent resistivity is 47 ohm meters. But that really is just a reflection that I have this conductor there. Take the sphere out, do the modeling, I still got 47 ohm meters. So this is a good place to leave this, right? Because I've got a problem here. I've got a mineral target. I've got something else that I'm looking for. I've got a resistive layer on top. I'm not going to see it with a DC survey, so I got to do something else. And that something else, of course, is going to be our inductive sources. And yeah. So we're going to break for coffee, come back and do the EM fundamentals, and then some inductive sources. 15 minutes for coffee?
If we could point it to screens. I don't know how we can do that.
Oh.
I can kind of just point to
Sí, ya me dijo. Okay. Are we live? I think there's no such thing as a 15-minute coffee break. I don't think you never do a coffee break unless you have. Okay, so we've looked, I mean, at this point, we've looked at DC resistivity and kind of got that under our belts. Concept of charges, as I said, is going to be continually important. And I think from the point of view of DC resistivity, once you think about the charges, then it really helps you understand about the excitation and also where you're going to measure. So I think there's a real benefit and an understanding that comes about there. We also saw in that last example that if you had a thin resistive layer over top, that can really destroy your ability to see anything with the DC resistivity. So now what we want to do is to show how we get over that using electromagnetic induction. So we're just going to go, first of all, some motivation. So let's suppose you've got a region that's 100 kilometers on the side, then your ability to do a DC resistivity survey is greatly, pretty challenging. We had this example that we showed before. Also, there's other things. You've got areas that are just hard to inject currents, or maybe you've got rugged terrain. So you really, it's really challenging for that to use DC resistivity. So what I want to do is to break things down. Again, my my approach to these things is always, let's make it as simple as possible. Get a foundation, and then maybe get another foundation. Then you put the two foundations together, and you can understand things more simply. So what we're going to do is to look at the various laws first, and then we'll put it together, and then look at just simple things like a sphere and homogeneous Earth, and understand about electromagnetics. But here's the basic experiment. We've got, let's say, a towed transmitter. So here's a transmitter that's going to put out electromagnetic energy. Here's a receiver. So the transmitter puts out a time-varying magnetic field. That time-varying magnetic field is going to induce currents in this conductive body. And those currents are going to generate magnetic fields that could be measured at a receiver. So that's the basic principles. What I now want to do is to kind of go through each of those step by step so that you have a really thorough understanding of what is going on. So let's look first at the transmitter. We could have a transmitter that's in time, like this, or frequency. If you look at many of the textbooks on electromagnetics, for instance, Ward Holmes, you see that the very first thing that they do is to look at things in the frequency domain, because then Maxwell's equations become easier to solve. And then they do stuff, right? And then they step over here, and then they do things in the time domain. And it's almost like it's two really, really different things. But they're not. It's the same physics. And what I want to concentrate on today is just like time domain, frequency domain just doesn't make any difference. There's some things that are important in practice, but the fundamentals are exactly the same. So that's why we're going to kind of continually be going back and forth, frequency to time. By the end of today, you're going to leave and really understand, like, okay, wait a minute, these two things are completely the same thing. Let's go back to Maxwell's equations. Now we've got a term here that is the time variation of the magnetic field with respect to, well, time variation of the magnetic field as on the right-hand side. So we've got this extra term and we need to include it. And what does that mean? So this says the time change of a magnetic flux, E, is actually going to introduce an electric field. So here's a source, and that's going to give rise to an electric field. That curl operator is somehow telling you that, well, it's going to be a circular electric field. So this thing here, this upside down triangle with a square across, is the curl operator. And our main thing is to take account of that. And that's going to be with Faraday's law. So let's first look at the equation that tells, well, this equation here, Ampere's law, which tells us that if I have a current, J is a current density, so amps per meter squared, it's essentially current. A current gives rise to a magnetic field, but again, it's a curl, right? So if I have a current that's going along, then it's going to generate a circular magnetic field. That's Ampere's law. And that everybody is used to, right? If I have a current that's in a wire, and then you describe the magnetic field with this right-hand rule, right? Remember, point the thumb in the direction of the current, and the circularity of that magnetic field goes around that wire. So here's the expression for the field from just a constant current. If I take that wire and I fold it in on itself, so I make a loop, then I get a magnetic field that looks like this. So it's got these circular things like this. And it's got a formula that looks like this. The important things about this is that the magnetic field, first of all, depends upon M, which is, it's called the magnetic moment. And that magnetic moment is the product of the current that's in the loop and the area of the loop. So that's an important thing to remember. Also, that the magnetic field falls off as 1 over r cubed. So this quantity here that we're seeing is the magnetic field of a loop, but that's exactly the same as if I had just a little bar magnet here. So if I had a little bar magnet in here, then you'd be able to sketch out the magnetic field lines that look like that. So the strength of that bar magnet is given by this, the magnetic moment, and then there's these terms here that tell us how fields can occur. So that was Ampere's law. Now we go to Faraday's law that says this time variation of the magnetic flux gives rise to an electric field that's got a current. And there's also a minus sign in here. That minus sign is very important. It comes from a guy by the name of Lenz. And it helps us determine which way the currents are going to be flowing in this one. And our procedure is that this time-varying magnetic flux is going to give rise to this electric field. And if the material is conductive, then there's going to be a current density that's equal to the product of the conductivity times E. So if I have a time-varying magnetic field, it gives rise to an electric field everywhere. Okay, but if there's a certain portion that is a conductor, I'm sorry, I've forgotten your name.
I think.
How do you spell it? Pardon me?
Esmeralda.
Esmeralda? Okay. Well, okay. Esmeralda. Okay, got it. So if Esmeralda is a conductor, okay, you are, right? Then you're going to have, there's going to be a current that's going in you, right? And the direction of that current is, so first of all, the current is going to be circular, and the direction of that current is going to be determined by this minus sign. This is an example then of how magnetic induction works. So here's a bar magnet, so there's a north pole and a south pole, so there's going to be a magnetic field that generates from that. Here's a coil of wire. That coil of wire is connected in a circuit. It's got a light bulb, and then there's a voltmeter in here, and completes the circuit. Okay? So, in steady state, we have the following situation. So here's a magnet. It's steady. Nothing is happening, but there's still a magnetic field that's going through here. And the thing that's important is called the magnetic flux. So that's the integral over the area of this coil of B, magnetic flux density, and the normal component of it. So we have the magnetic flux that's going through here that depends upon the strength of the magnetic field and its orientation with respect to that coil. The induced EMF, or the induced voltage in this circuit, is governed by the time rate of change of this magnetic flux, according to this. So the voltage, or the EMF, is minus the time rate of change of flux. And in this case, since nothing is moving, that's equal to 0. I effectively have a circuit that looks like this. The voltage, resistor, some inductor, and there's going to be a current in it whenever there is a voltage. Okay? So now what I'm going to do is I'm going to move this magnet. I got to push it in. Okay? So the moment I push it in, now those lines of flux, they're stronger. The magnet's closer. So there's more flux through, so it's phi B is increasing. But I look at the rate of change, and then with the minus sign, so the voltage has decreased, is negative, so it's over like this. But there's still a current in this circuit, and the light bulb is going to go on. If I go the other way, now I pull it back, then there's another change in the magnetic flux, and so the voltage that's in here is now positive. So the current's going to go the other way, but that's okay. The light bulb is still going to go on. So that's essentially the idea. As long as I'm changing that magnetic flux through something, I'm going to get an induced voltage in energy. We have a couple of apps to show that. They're simplified. They're two coil apps. There's a red line here, so that's a primary. Here's our primary substrate P. So that's a primary. There's a current that flows through here, a primary current, and that gives rise to a magnetic flux, and that's going to impinge upon a target loop inside. And then there's going to be a secondary current that's going in here. This target loop is characterized by a resistance R and a self-inductance L. Okay? So that's going to be our circuit. Now we have apps both for harmonic currents in here. So that's what this diagram is. I'll explain that in a bit. And we also have one for the time domain. So these are things, again, that you can play around. You can get them. Let's look first at the time domain. So in the time domain, what we're going to do is we're going to have a constant current in the primary loop here. A constant current. It's going to step off, and then it's going to be zero. The flux follows the same manner. But the time rate of change is just an impulse. It's like a delta function. And the moment that I turn that current off, then there is a current that's going to be induced in this loop here. So that's our secondary current. And then that is just going to decay away. So we've got a current going through that circuit, but there's a resistance. So it just decays away to zero, so that my secondary currents will go like that. Okay, so that's what happens if you have just a transient pulse. The quantity that people are usually referred to is something called the response function. And for the time domain, it's really simple. The current as it's going around, so it's first induced in this secondary, in the target, has an initial amplitude, and then it decays away with a time constant tau, where tau is equal to this ratio of L upon R. L is the self-inductance and resistance. So if I look to characterize how those currents are decaying in my target body, I see that if I plotted the response function as a function of time, that it would just be linear and have different slopes depending upon whether I've got a small or a large time constant. So here's what my response function looks like for a time domain response. It's very simple. It's just an exponential decay. That's plotted on a log linear plot. If I plot it on a linear plot, then you just see the exponential decays and curves. Okay, so the time domain is really simple, right? I flash, I make an abrupt change in the magnetic flux, and then that just induces a current, and then it goes, just decays away exponentially. What happens if I have a harmonic signal? So now instead of a step off, I've got something that's oscillatory. Well, it's the same physics, so things shouldn't really change, and they don't very much. The thing that's complicating with a harmonic signal, so let's look here at the signal. So the red is the primary. So that's what's in the outer loop. So it's just a harmonic signal that's going like this, right? So what's the current that's going to be induced in Esmeralda, right? So she's you know, just got currents, but there's always this, it's always changing, right? The primary flux is always changing, right? So you can't catch up like a nice exponential decay. But the only thing that can happen, because the primary field is going at a particular frequency, the currents, as normal, also have to be going at a particular frequency. They don't have any choice, right? So somehow it has to operate as cosine omega t. So the only things that can change then are the amplitude of that current and maybe its phase shift. So here's what the current looks like in the target light. It has the same frequency. It's got different amplitude. And notice that there's a shift here in the phase. Okay? That's all that happens. But we could take this green curve here and we could represent that as the sum of two things. We could represent it as something that was in phase with this primary. So starting up here, it starts up high, and down. So this would be the part that's in phase. And here's the part that is out of phase. So I've got something that's going like this. Okay, so now I could have, it's really hard. Okay, so I've got something that's going like this. It's really hard. Now I've got, something like that. Okay, so it's okay, and then I could also have something that's going like this, and then be something that's kind of out of phase with this, right? So I sum these two guys together, and I get this green curve here. So the only thing about the green curve, the secondary currents that are in that loop, is that I can represent them as a part that's in phase and a part that's out of phase with my primaries. Okay? So that's good. We can actually do that mathematically. So I can take my secondary signal, current, it's got some amplitude, and it's got to be like cosine omega t, and it could have a phase shift inside. But there's an expansion for this. I can write cosine of difference between two angles in this particular form here. One that depends upon cosine, and the other which depends upon sine. And so that's the issue. So the amplitude of this guy here that depends upon cosine, cosine is the same as that. So we call that the in phase, or sometimes we call it the real. Doesn't matter. Same, two different words, exactly the same thing. So that's my in phase. I've got this part out here. It's a sine, so it's 90 degrees out of phase from the cosine. And so I call it the out of phase part. I call it the quadrature. I call it the imaginary. These things here are probably the greatest source of confusion for anybody who is in electromagnetics to talk to a geologist or somebody else who's not, even a seismologist, right? When the controlled source EM came about for marine EM, I was at one of the initial SEG conventions when this was kind of coming out of the box, and there's all these seismologists that are like, what the hell is going on? These guys are talking about imaginary data. Like, give me a break, right? But there's a historical reason why these all kind of make sense. But from the point of view of understanding, you just have to remember that they all mean the same thing. And honestly, sometimes in the same sentence or paragraph, I'll use all three of these just interchangeably. It's just like resistivity and conductivity. You just get so used to them. Here, people talk out of phase, quadrature, imaginary, all the same. It's the same. What about this phase lag? So there's an expression within the context of a circuit that the phase is this omega L upon R. That's called the induction number. That's a very important quantity because the phase here depends upon all three of those numbers in that manner. If I change L, R, omega in such a way that this number stays the same, then that phase difference is going to be the same. So it's a dimensionless number. So we can plot what this is going to be like. We could plot the real part and the imaginary part as a function of induction number. So that's what we're going to do here. So when the induction number is small, okay, we get these values here. So the dashed line is the out of phase, or the quadrature, or the imaginary. And the solid line is the real. As I change this induction number from very small to very large, notice how the response changes. At small induction numbers, the imaginary part starts to be really large compared to the real. So most of the information about conductivity is actually in this. And there's some instruments out there that actually operate in exactly with exactly that idea. Right? And then as induction number increases, the real part gradually overtakes, and eventually at very high values of induction number, which is often called the inductive limit. We're up here where the response is purely real and there's no imaginary. So this part here is called the inductive limit. This part here is called resistive limit. And you'll hear people talk about those two things. So to summarize, response function, step off, harmonic, time frequency, they're both the same. They both follow these Maxwell's equations here. And yeah. So now we've got currents that are set up. Okay, so that was the first part. So we can time varying flux sets up the currents. And now what are those currents? So now we've got the currents. So that's going to give rise to a magnetic field. Remember, it's a curl, right? So we're going to measure these magnetic fields at a receiver. The question is, okay, what do we use for a receiver? Well, we have choices. We can measure B. So that's the magnetic flux density. And we could do that with a flux gate magnetometer. Or we can measure dB dt with a coil. So again, if I have a coil, and I've got a time-varying magnetic field that's going through, that's going to generate a voltage in that coil, and that'll be my response. So most of the airborne instruments are actually dB dt. A lot of the ground-based instruments, some dB dt, some B. The important thing is that each of these coil systems only measures one component. So if I wanted to measure 3 components of B, I'd need to have 3 flux gate coils, or dB dt and 3 components, I'd then have 3 coils. Again, coupling comes into play. So remember, as we're talking about, so let's suppose here's our transmitter. And think about these objects here as being our target loops, right? So if I have a target loop that's sitting right here, then I'm really perfectly coupled. The magnetic flux from this one is coming right down through here. And so my integral of B over that area is really high, so I've got perfect coupling. I also have really good coupling if I'm like this. So as long as my magnetic flux is coming in perpendicular to the coil, I'm fine. But notice if I'm up here, I don't have coupling. I've got a coil, but my magnetic flux is just coming parallel to the coil, so there's nothing crossing. It's called null coupling. So depending upon the orientation of your transmitter to the target, you have either good coupling or not. The other thing is that we have currents in the target. So I've got, if there's currents flowing in Esmeralda, there's magnetic flux coming out here, depending on which way I am as far as I'm a coil. If I'm standing like this, I've got perfect coupling. If I'm like this, I got nothing. Okay? So the coupling happens 2 ways, from the transmitter to the target. And in the other way, if that's the target current, then that's your receiver. There's the same thing. So there's 2 couplings. if you look at any work on electromagnetics, this is probably one of the formulas that you're going to see, and that's the ratio, if you have an airborne system, of the secondary field to the primary field. So that is actually what's measured. When I first looked at that, I thought, wow, that's really confusing. It's a lot of stuff going on. However, with what we have now, from an intuitive point of view, we could actually we could almost write that down just right from scratch. And I'll show you how that works. So here's our geologic system. I got a transmitter, I've got my conductor in here, and I got a receiver. So we're going to represent that in terms of 3 coils. We've got a transmitter loop, we've got a target loop, and we've got a receiver. So now let's look what happens. So I've got a transmitter loop, so it gives rise to a magnetic field. And there's going to be currents that are going to be induced in here, but the main thing is going to be the coupling between this coil and that coil. And we can relate that by this quantity M. I will subscript it 1, 2. And that depends only on geometry, right? Remember, coupling is just geometry. So here's a formula for the coupling. So that gets you from M1 to M2. Now I got currents in here, so they're the source. And here's now my receiver. So I now have another coupling, M23. So this is getting kind of energy from the transmitter to the target, from the target back to here. If I look at what's going on here, I've got a transmitter. It's giving out a primary signal, and that could also be measured at my receiver loop. So there's a coupling here, M13. Okay, let's put all that together. So here's HS over HP. So HS, my secondary field that I'm going to measure. Well, how does that come? I've got to go this coupling down here, M12, got to get up there, M23. So that's what this is. So M12, M23. If I look at the primary, well, if I look at the primary, I'm just going from here to here. So that's just M13. So you can see this stuff in here is just to do with the coupling. But now I've forgotten about, wait a minute, I've got a response function in here. In my target body, okay, I've got a response function. So there was this in phase, out of phase part. So I need to count for that response function. That's what this guy is here. Here's the response function of the target. So how intuitive is this, right? HS over HP, here's the couplings, here's the response from the target, and here's the primary field. I got it, good to go. And if I plot that up, here's my target response. Okay, so now let's just take you through what would happen. One of the things that a typical system might be like this. So we've got a transmitter, receiver. Has anybody here used something called an EM31? 1 or 2. Anybody used a Maxwell or any kind of thing that's sort of fixed transmitter and receiver that you're just towing along? Which one did you use? Or? Okay. Yeah, so there's the system I want to look at is it's just a fixed transmitter and receiver. And again, we want to plot the responses. So there's a red line and black line here. They're superimposed. We're not going to worry about that. But what we're really interested in is the shape of this. Where does this shape come from? Well, we have to kind of break it down a bit. So in this case, both the transmitter and the receiver are on this side of the target. So let's just think about the transmitter first. So the primary field is going to come down in through here. So the primary field comes down into the target. It's time varying. So that means that there's going to be a current that's going to generate in here. The current's going to go around the loop, and that's going to give rise to a magnetic field that goes back up. So on this side of the loop, when the transmitter and the receiver are both here, the primary field is up this way, The secondary field is up this way. And because they are in the same direction, we're going to say it's positive. Okay? So again, if I'm looking for a target, sorry Esmeralda, to use you again. If I'm sitting on this side, okay, the primary flux is coming in, there's going to be current in you going one way, it's going to kind of oppose that. So both the primary and the secondary field here are positive, and that puts me up in here. At some point, I'm going to come over like this. So if this is my receiver, the transmitter's still back here. So there's still currents going in you the same direction. But I'm actually going to receive a point here. Notice there's a zero crossing. So why is there a zero crossing? Well, that would be a minus. That's actually what's going to happen here. Why is there a zero crossing? Yep. Yep, what? No coupling, right. So my coil is here, magnetic field is parallel to that, so there's no flux. There's no flux coming in here. So that's my zero crossing. Now I come like this, transmitter this side, receiver that side. Now we come to your situation. Primary field is like this, but the magnetic field is going down. So that's opposite. And now I get a negative. And now I come over like this. So here's my transmitter. Here's my receiver. What happens here? I get a zero crossing. Why is that? Pardon me? There's no coupling. Now, but different reason, right? So now the magnetic field from my transmitter is coming in, perpendicular to you. So there's no flux cutting through you. So now there's no currents. Before there was a zero crossing, there was lots of currents in you. Now there's a zero crossing because there's no current. Then I come over on this side, now they're both on the same side. Okay, so that tells you why there's this shape. So all of that is shape. That's just coupling. Now let's look to see, okay, I've got the real and imaginary parts. In this particular case, my induction number is equal to unity. So the real part and the imaginary part are identical, and so they plot on the same line. Okay? If you actually understand this line, you actually understand a lot about fundamental principles of electromagnetics, because you can sketch out which way the currents are going in a target, which way the fields are going. There's a lot that's involved in doing that. And now you're now interested in, okay, what's the real and imaginary parts? In this case, here's your response function. You see that they're equal. If I change this to have a lower frequency or lower induction number so that I'm on here, now look, so now my imaginary part is actually larger than the real. And that's what I get. So here's now what I expect if I go over a target with a different induction number. So it could be that it's a less conductive target, more resistive. So it looks like that. And if I go the other way, so I'm over here, now the real part is larger than the imaginary. Okay? So the shape is more or less just due to geometry. The ratio of the real and the imaginary part is change in the induction number, so that's omega L upon R. Okay? Now let's go back to the time domain. What happens in the time domain? Geometry is the same, so if I'm going to measure something at a particular time channel, I'm going to expect exactly the same shape, because that's all geometry. But my response function, remember, was this exponential decay, so it's this. So what all that means is that if I do the same experiment but with a time domain system, I'm going to get time channels. So now I'm walking along looking at value in a particular time channel. At early time channels, it's going to be larger because I'm earlier in time, so I hasn't decayed as much. At later time channels, it's going to be less. So I'm just going to get a sequence of curves that look like that. Frequency, time domain, completely understand. Okay, so what have we learned? Well, we know something about basics of EM induction. We've got the response functions for frequency and time, mutual coupling, and we've got data for frequency and time domain system. And also that the circuit model, it seems like, okay, that seems like not such a bad idea. But the question is that applicable to a geologic target? So let's see, let's test it. So we're going to do a numerical simulation. We're actually going to take a sphere. It looks like this. So it's conductive, 2 Siemens per meter, 30 meters in radius. And we're going to have a transmitter that's sitting right above that sphere. And then we're going to look at the response at a receiver that's 8 meters away. If we work on this side with the circuit model, here's the response that we obtained, just the classic. If we take this and numerically model it, then we end up with curves that look like this. So you can see that they're basically the same kind of things. You see how the character of those things change. So that means that the circuit model is probably an okay thing to just ground yourself in understanding the problem. So how do we do the numerical modeling for that? So it's built on a package in SimPeg. It's open source software. It's available through here. And Lindsay has been the lead role in this. There's 2 papers. One is by Crockett et al. The other is Lindsay with respect to the EM. And this is it's a cylindrically symmetric code. So it can work in anything in which you have cylindrical symmetry, and this code is made available to you. And what that allows you, why it allows you to do the sphere, is that if I have a transmitter that's directly above target, again, if I could use Esmeralda as pinpoint, so now if you're spherical and I've got a transmitter loop here that's circular, then we can make everything all symmetric, and we can actually solve this kind of 3D problem to find out where the currents are and all of the fields. So this is a really valuable piece of software, and it's used at the heart of a lot of the apps that we'll present. So we're actually getting in pretty good shape. We're kind of understanding the problem, but there's something that we haven't really talked about yet, and that is getting the energy from the transmitter down to the target and back again. So now the question is, how do EM fields and fluxes behave in a conductive background? And for anybody who's doing magnetotellurics, this is a bit of your bread and butter, if you like, of what's going on. So we'll go back to Maxwell's equations. In first order, they can be written like this. And we could combine these into a second order differential equation. It's got a couple of terms. One like this is a diffusion term, and the other is a wave propagation term. And in the frequency domain, we can write them like this. It's called a vector Helmholtz equation. So we take this and we write it like this, and the quantity that's important is this K. A K is a wave number. And in its full glory, it looks like this. There's 2 terms in here. And for low frequencies and the conductivities that we're usually dealing with, generally this term here is much less than 1. In other words, this term here is generally, we can neglect it, and then that's called the quasi-static approximation. For most of what we're going to do today, up until we do GPR, we're going to be in this domain. Under those cases, K then reduces to this quantity here, which has a real and an imaginary part. What we're most interested in, so now we take this wave number term and we put it into here, and we get actually, the thing I neglected to mention is that what we're now going to do is assume that we have plane waves coming in. So what do we mean by a plane wave? It means a wave that's got a constant phase at an amplitude at each point on the plane. So we can imagine how we could do that. Let's suppose we just had this big sheet of current above us. So all the current, maybe it's all going in that direction, right? So we've got current that looks like that. Then the magnetic field is going to be perpendicular to that. It's going to be like this. And the electric field is going to be in the direction of the currents. And then everything is just going to propagate down like this. So there is a magnetotelluric app that we have, and it actually does this plane wave solution. So here now we've got H in this way, E in this way, and then it propagates down like that. In those conditions, when we have this quasi-static, the result is that the magnetic field at each point depends upon initial amplitude, and it's got two terms. There's this term here, which describes the phase. So it's a propagating wave, it's got a phase. And it's this term, which has got an attenuation, it goes e to the minus alpha upon C. This term here, if we plot it, has got a natural decay that looks like this. So this is Z in this direction, and this is amplitude. So at the surface, it has an amplitude of 1. And then by the time that wave has decayed to 1 upon E of its value, we say, oh, that's what's called the skin depth, delta. So this is an important quantity in the frequency domain EM. It's called the skin depth. It's given by this equation here, or we could write it in terms of conductivity and frequency. So that determines how far a wave can propagate into the Earth before it decays to 1 upon E of its value. What happens in the time domain? So in the time domain, our equations look like this. From our perspective, there's two representations. The first is that we want to look at what happens if you're at a particular position in space and what happens with time. So again, let's suppose I'm a source here, and I turn off instantly, and now there's going to be a propagation of electromagnetic energy into the medium. Initially, when I turn this off, Esmeralda doesn't feel anything. There's not had any time to get anything. So there, if we're looking at what happens at your position as a function of time, this is what we see. Nothing happens, and then the amplitude of the magnetic field increases at time, in this case, 0.02 milliseconds, it reaches a peak, and then after that, it just decays. So for any person sitting in the room, the moment that I turn the system off, you don't feel anything, and then there's a sharp increase in the fields, and then it just gradually decays. So that's what you're going to see if you're an observer sitting. The other thing we could do is, after a particular time, I could just take a snapshot of what the magnetic field looks like. And it would actually look like this. So now this is depth, this is the amplitude, and this is at a particular time. There's a peak here at a particular depth, okay? This thing, the peak is at a particular time, the peak is at a particular depth. We refer to that as the diffusion distance. So that is governed by the time and the conductivity of the medium. And it's given by this equation. So if you're, and generally EM people will talk about, oh, at a particular time, with a particular conductivity, the wave has diffused into the Earth this amount. Okay, that's a good thing. You can see that that's only, you know, it tells you some information, but it certainly doesn't tell you all. So you can see that, you know, there's magnetic fields before and after. But the propagation of this peak as a function of time really does tell you kind of how that energy is diffusing into the Earth. So we've got two things. In frequency domain, we have the skin depth. In time domain, we have diffusion distance. Those are the two things that are important on a regular basis. So we've got apps. There's a plane wave app. This is really good for magnetotellurics. So you can change the number of layers and conductivities and look to see what the fields look like as you go down into the Earth. So let's look now at the effects of this background resistivity. So we had our transmitter. We want to get energy to the target. And remember, it's going to attenuate, get response, and then we got to get material back up, so there's energy going to attenuate there. So now we're getting towards the complete solution. So here's an example. Let's go to the time domain first. Actually, this has been kind of interesting for me, especially, is we decided, okay, going to put together a course on electromagnetics, and then what's the simplest way that things can be explained so that, you know, it just makes the whole process easier. And it became, well, it became evident to me, but especially after a talk that I had with a GPR expert, Peter Annan, if anybody knows that name. And he was saying, you know, he's tried to teach electromagnetics, and he's always, he can never do it successfully, easily, in working in the frequency domain. He says the easiest way to do it is in the time domain. And that is 100% true as far as I'm concerned. So what I'm going to do a lot is we'll talk about time domain. That sets up the physical intuition, and then we can go to frequency domain and see, like, oh, I got it, I got it. So here's where we are. So let's suppose we've got our sphere here, conductive, and it's got this really resistant background. When we turn that system off, then we get currents that are on the outside of this body. So that's kind of interesting. We're exciting the body, because where your currents are is where your excitation is. But there's actually a couple of things that are interesting here. Actually, there's quite a few, but I'll only talk about it. So first of all, you know, we only have currents that are just really on the outside of this object. And yet, you know, we kind of effectively got sort of a plane wave coming down. And, you know, so maybe the first question is, like, why don't we see like currents inside here? Anybody? Why are the currents only on the outside? So what we're looking at here is we have a system, we've turned it off, and this is at 10 to the minus 5 seconds, 10 microseconds. And we look at the currents, and they look like that. Perfect. Remember I talked about diffusion distance that depends upon the time and the conductivity. So at this time here, which is very early, this material here is very conductive. So the energy has only had a chance to diffuse into here a certain distance. Or if your comment was in high frequency, which is essentially the same. So that's, it just simply hasn't had time to get into there. Okay, so that's kind of like a really important insight. Like, okay, why is the current around the outside? Well, it's because this is a high conductor and there's a diffusion distance at this particular time is only a meter or 2 meters. Okay. So now let's change things. So let's now put in a background conductivity. Okay. So instead of 10 to the minus 8 meters, Siemens per meter, which is sort of free space, let's increase it to 10 to the minus 2 Siemens per meter. Okay, so now what's going to happen? Remember we were talking about energy loss. So what's going to happen if I increase the background conductivity to 10 to the minus 2 Siemens per meter? Yeah, so the fields might be up. Okay. The comment was that currents will be near the surface. Anybody else? Well, let's try it. So now I'm going to increase it to 10 to the minus 2. And what's happened? Not very much. It's still there, right? So why is that? I've now made the background more conductive, 10 to the minus 2 Siemens per meter. Yeah?
It's not conductive enough.
That's right. So it's not conductive enough. The diffusion distance of the primary filter here is still huge. So I've increased the conductivity, but I haven't made it. But now if I increase it more, now we come to what you see. So you can see that, okay, the Earth is a conductor. So I got primary, here's my currents that are induced in the Earth. There's still stuff getting through. I can see the sphere a bit. But if I increase it more, now I've just got currents that are right up at the top. Okay, so everything is in accordance with, diffusion distance rules, and you can kind of see what's happening. In free space, it looks like that. Increase the background, but it's still resistant. Now I make it. This is what you consider to be a conductive background. You're really shielding yourself from here. A lot of the currents just come from here. And then if it makes it really conductive, then you're okay. So that's what happened in the time domain. What happens in the frequency domain? Well, I've just been arguing the time domain, frequency domain should look the same, right? So now let's look at a high frequency, 10 to the 4th hertz. So we're going to fix that. Okay, here's my system in a background of basically free space. Here's my current density. Now I increase the conductivity here. Same thing, right? It's still 10 to the minus 2 Siemens per meter. Still get pretty much the same. Increase it to 0.1 Siemens per meter. Now I have currents that are induced here. Still see something there. Increase it more, they're all up here. So this is all at one frequency, 10 to the 4th hertz. The previous stuff was all done at one time. And these pictures look identical. If I had plotted frequency here, if I said time, you'd agree, like, okay, that could be. So that's basically it. I think we're now ready to look at some field examples. So here's the case histories that we're going to try to do today. We'll see. I think we can get through most of them. So we're going to start, we started off, we've already done this one. This is the Mount Isa mineral exploration. We're going to do example for time domain EM looking for paleo channels. This is groundwater for Denmark. The Wadi Saba, this is the use of airborne time domain EM to get a better conductivity model so that you can actually help with seismic corrections for seismic data. This comes from Saudi Arabia. There's a frequency domain experiment looking for salinization of water, so that's another groundwater problem. Also the same technique, frequency domain for landslides. So these are inductive sources time domain. This is inductive sources frequency domain. Then we have grounded sources. So there's a tectonic problems and then a hydrocarbon de-risking and methane hydrates. Probably can't get through all of these today, but if people are interested, we can flip through them and talk more about them tomorrow. For geothermal, and so for natural sources, magnetotellurics, so there's geothermal energy, and off of Iceland. And then there's, in Sweden, there's landslides caused by quick plates. There's also for natural sources, a mineral deposit, Santa Cecilia, that uses control source CSAMT as well as MT. And then SEDTAM, which I think is of interest to the group here, both a synthetic example and a mineral exploration example. And then GPR, we've got some geotechnical studies as well as self-driving vehicles, which is kind of interesting. And then we come back to IP and its use for landfills and wound up with our lives. So it's quite a few case histories. We'll see. It's, you know, you're here until 6, no problem. Oh, we could do 7 if you need. Okay, so let's do inductive sources. Sure. Oh, lunch is at 12:30? Okay. So notice that, see, at some locations we were starting at 8, which meant that, you know, we'd do all of inductive sources and then have lunch. But here we started at 9. So the little tool for the lunch box is, we're only going to get partway through this. Okay, so what's our motivation? Again, these guys here, large areas to be covered, shielding problems, rugged terrain. We're going to go through a basic, the basic setup. So here again, if you've got, and geophysics is likely, you always have a lot of questions. Okay, so the first is, okay, what's the target? Is that surface? Is it a depth? Is it 1D, 2D, 3D? Okay, what transmitter do I want to use? Is it on the surface? Is it in the air? What's the size? What's the orientation? I have to worry about coupling, right? How do I excite that target? And which fields do I want to measure? What instrument? I mean, where to collect the data? All these things. What's the depth of investigation? There's just a ton of questions, and you actually have to answer all of those if you're going to do a serious survey. So these questions are all really part of survey design. And as we just see, the basic experiment, we already know, we got a transmitter, time varying fields, get currents in here, get the fields at the receiver, working time. So let's first of all think a little bit about the transmitter. So if we've got large areas or rugged terrain, then ideally we want to do an airborne survey. So that could be with a frequency domain system, like this result, or it could be a time domain system, like the SkyTem. So that's sort of method of choice. These guys are becoming more and more popular. If we have a really deep target, and I've got a example here, case. So you got some deep targets. Then we need to get energy down deep. So we need a big, strong transmitter, big magnetic moment, which means area times the current. So this is actually a loop on the ground that's a couple of kilometers on the side. So it's a big loop, but if you're going to look deep, you're going to look a kilometer or a kilometer and a half down. That's one way of doing things. So just a couple of things about the transmitter. Generally, they're kind of like a loop source. Even in this guy here, where he's 30 meters in diameter. By the time you put him up there, and you're looking to see what's down, it looks pretty much like a dipole. And here was the expression that we had for a dipole. And the important thing was the magnetic moment. So that's the current times the area. But the other thing you could do is wrap a couple of coils around. So you loop it around twice, times the number of turns. The field falls off as 1 over r cubed. And then there's all that attenuation depending upon the background conductivity. And you want to be as close as possible as you can to the body. So the closest that you can do is a ground-based system. Then you might go up a bit with a helicopter or farther away with a fixed-wing aircraft. So those are your options. And then you're always concerned about coupling. What kind of a target you're looking at, the geometry, and how is that going to relate to your transmitter. Your data, we talked about these before. You can measure dB or dB dt in that receiver. In the time domain, the advantage of the time domain is that you're measuring in the off time. So here was typical transmitters might be something like a SkyTem system. So this is a loop. It's about 30 meters in diameter. And the receiver is actually sitting right up here. So it could be sitting there. In this previous, in some of the other towed systems, or the receiver is sitting in the middle, or down here. So those are your receivers. The other thing is that the receiver could also be airborne. Here's an example that I showed you before. Here's a large time domain system. There's a loop out here, a couple of kilometers on the side. And the receiver is actually a total field magnetometer that's being towed across here. So the transmitter's on the ground, receiver's in the air. All possible combinations work, right? In the frequency domain, the systems are usually like this. So here's an example. Here's a resolve system. You got a transmitter loop here and a receiver loop here, and each of those combinations is for a particular frequency. So in this case here, there's 5 sets of coils, and there's 5 frequencies. The difference between the time domain and the frequency domain is that in the frequency domain, the primary is always on. So that primary field that you measured here, so here's your transmitter, so you get a primary field that's always on, and it's big compared to the secondary fields that you measured here. So somehow you got to get rid of it. You have options that you could compute what that primary field is and subtract. The other is that you can try to cancel it out with something called a bucking coil. So here's a small coil that's right next to the receiver loop that actually puts out a magnetic flux that's equal and opposite to the primary field that's coming in. So it kind of cancels it out. And then what you measure is just the secondary field from here. So those are your options. The main thing is very often that you want to make sure that the transmitter and receiver coil are at a known distance and fixed geometry with respect to each other. And here was that EM31 that operates just on a boom, and you carry it across, and you just measure the secondary fields. So some of the next questions has to do with how many data to collect, how accurate, depth of investigation. What's the footprint of the transmitter? That's an important thing. These things are all kind of survey design. So let's take a little bit of a look at what's going to happen. So let's look, first of all, look in the time domain. So we're going to have a current that's on and steps off. So if we're measuring with a B field receiver, the magnetic response would look like this. If we're measuring with a coil, then there's an impulse and then a subsequent. What I'm going to step you through now is a sequence of images that take a look at what the currents are doing in the Earth. And we're going to work with what's called a vertical magnetic dipole. And where that comes from is that the transmitter is going to be a loop, right? So a loop of current. A loop of current gives rise to like a magnetic field that's just like a magnet, a dipole. And the orientation is going to be such that the loop is parallel to the Earth's surface, or the vertical magnetic dipole is perpendicular. So that's where EMPI comes from. So we're going to look at just a loop over a homogeneous Earth. And here's our example here. So we're going to have an Earth, the flight line is going to be 20 meters above the surface. And our question is, okay, where's the currents? How strong are they? What's the effect of conductivity? And what are the fields of? So we're going to use this. Again, this is another app that you can play with. So here's a three-dimensional model. There is, we can view either in plan view or we can view in cross sections. So what we're going to see is a depth, and then here's our source, and our half space is going to be 100 meters. So first of all, what do the currents look like? So I've got this guy up here. So here's the transmitter. So I've got a current going in here. And then what are the currents going to look like in here? So I've got currents going here. I turn them off. That's going to induce currents in the Earth. Okay, how are they going to travel? Well, first of all, if I look at plan view, those currents are going to be circular. They're going to be just the same as the current in the transmitter. So they're going to go around like that. And if I get a cross section, it'd be a place that the currents are kind of coming out and they're going back in. So the currents in the Earth are circular. So at any one cross section, some are coming out. So that's what we're seeing. The magnetic field, so here's my currents. So what are my magnetic fields going to look like? Well, since what we've got for currents are just like a whole bunch of current circular filaments here, and you know that for each coil, there's going to be a vertical magnetic field, then you can see that the main part of the magnetic field, the high values, are sitting right in here, kind of at the midpoint of where all these currents are coming, right? So each of these guys are going around. So that's my magnetic flux. I'm going to measure them not here where they're most intense, but I'm going to measure them up here. So actually a few meters away from my transmitter location. So the little red dot, if you can see it, is where I'm going to measure my magnetic field. So what happens as a function of time? So we're going to turn things off, and now we're just going to concentrate on this side here, where we're looking at the where the currents are as a function of time. So this is at a very early time. The diffusion distance is only 18 meters. And you can see that the currents are kind of... little later, currents are like that. Later, they diffused out, so diffusion distance here is 75 meters. Here's 132. So what do we see with that? We saw that the moment I turn that current off in my transmitter, I get circular currents in the ground, and they're going to kind of diffuse downwards and outwards as a function of time. And this is how they're going to diffuse. So you can see how they're going. And what's interesting about that is that there was a very famous paper written by Misak Nubigian back in 1979 that was trying to find some way of, okay, how do I understand what my magnetic field should look like from these induced currents? And he came up with the idea of smoke rings. So these were basically rings of current that kind of diffused downward and outward along a trajectory that was something like that. And what this does is kind of encapsulate that. One point that is, I should mention here, like we see these kind of blue and yellow colors. That's done so that we can present things. The scales here are very different. So this is 10 to the minus 7, that's 10 to the minus 8, that's 10 to the minus 9. So here's the concept I want you to go away with. I establish a current in the earth, and as a function of time, it just kind of diffuses away. The amplitudes decrease, the breadth increases, and eventually they just disappear. That's what happens with time. So those are the important points. Currents diffuse downwards and outwards. So each transmitter has got a footprint. So by looking at where the currents are at a particular time, that's your information about understanding what's going on. The maximum resolution that you get is going to be controlled by the earliest time. So your smallest diffusion distance is given at the earliest time, and you saw that the currents are kind of concentrated near the surface. That tells you something about your maximum resolution. Your latest time tells you something about how deep you can possibly see. So those are two kind of pieces of information. Have you got time for, I think she's 12. I could do this one, but maybe 5 minutes later. I want to do a layered earth because that'll kind of get your mind going over a lot. So now we're going to do some an earth that's got a layered space here. So there's going to be basically a 100-meter background, but there's a layer here that's 20 meters thick that I'm going to make either resistive or conductive. And we want to see, okay, if I put a layer in, what's going to happen? So we're first of all going to look at things in the time domain. So here we got a background of 100 ohm meters. And now the question is, if we, let's see which way we're going to do. Yeah, oops. I was going to ask you the question. So I lost it. So we're going to put in a layer. We're first of all going to make it a resistive layer. So this guy coming in here, it's going to make it resistive. So instead of 100 ohm meters, it's going to make it more. So what do you expect is going to happen if I put a resistive layer in there? Since I showed you the next slide, go ahead. Somebody? So I'm going to put a resistive layer in. How is that going to? Here's the currents that I have with just a homogeneous half space. Now I put a resistive layer in here. Then what's going to happen? Yep.
That would be a smaller current than the resistive layer, but only in the resistive layer.
Good. It's going to look like this. So I still have an electric field everywhere, but the currents in here, because they're on Ohm's law, is really small. So that my currents for the resistive layer actually look like this. And you notice also that I'm actually seeing a little bit deeper than I was before because current things are not being attenuated here. So that's what's going to happen if I put a resistive layer. Okay, now what happens if I do a conductive layer? That's good, somebody's got to do it.
Currents will focus in the conductive layer.
Right. So here's what happens if I have a conductive layer. So most of the currents are actually in that conductive layer. And if I make it really conductive, then my currents don't even get all the way through that conductive layer. They're just attenuated. So exactly, you see, I mean, you're now getting to the point where, okay, this stuff is almost intuitive. I have a resistor, I'm not going to see anything. The fields are going to propagate right through unattenuated, and there's a consequence of that. If it's a conductive layer, it's going to get hung up and get attenuated. If we look at the magnetic fields from these cases, from the half space, if I put the resistor in, get something like that, put the conductor in, you see how the magnetic fields are changing, and you can see that that must have a reflection up here. The way in which that is made a bit more transparent is through what's called the sounding, your sounding curve for a particular station. So what we mean by that is, so this is your response as a function of time. For 100 ohm meter half space, you get this solid black. For 1,000 ohm meter layer in there, the dashed line is response with the layer. And you can see it just doesn't change very much from just the half space. So that tells you that if you're doing a time domain system over a region that's got a resistive layer in, you're not going to see that. On the other hand, if you make that a conductive layer, 10 ohm meters, you've got a very large difference here in that response. And if you make it really conductive, now you've got something like that. So these curves here with those responses tell you that, you know, if you're trying to find a conductive layer in a background Earth, that this time domain system is going to be really good. Whereas a resistive layer, you're not going to do so well. In general, we're going to look for a 3D object. So here's now a sphere. And what we're going to see in this map is we're flying this time domain system over this region. So the sphere this is a plan view map. That's east, that's north. Our sphere is centered right here. And these dots are the locations at which we have a sounding. At very early times, where the waves have not really diffused in, we basically just see this background resistivity. My response function is almost uniform everywhere. And if I fly along here, this is a profile along here. So this line here is the same as that line here. And you can see my response is basically uniform. There's no indication that there's a conductor there. A little bit later, I see on the plan view map something that looks like that. So the sphere is starting to kind of come out. And here I've got a little bit of a bump on my time domain profile. Here's a sweet spot at 0.3 milliseconds. That's what it looks in plan view, and profile looks like that. So now I've got a very high response over my conductive sphere. A little bit later, it started to attenuate. A little bit later, it goes like that. So here's the summary of my airborne time domain data. At very early times, it's uniform. There's a place where, you know, now the fields have decayed. They're in the sphere. They're causing a lot of extra responses. So I'm seeing them, and then actually after a while they decay. And that's what this scenario is being played out here. And this is what the profile curve. Generally, the contractor will provide you with a lot of these kinds of curves, where you just do profiles over a line. Some general time domain systems. Here's the SkyTem system. It's got a transmitter that looks like this. It's got two modes of operation. One's a high moment and one's a low moment. So high moment, you remember we need to see deep. The problem with high moment, if you have a big current in a loop and you try to crank it off, you can't do that. There's a lot of back EMF in there, and you just can't turn this thing off fast enough. So if you have a high moment system, then you can't record very early in time. In this case, it's maybe 47 microseconds. So then they have a lower moment system that you can get earlier. So now 12 microseconds. That means that you can get better resolution right near the surface. So this low moment system is really good for nearer surface material, and the higher moment for deeper. Notice that there's a waveform that's going in initially. So here's the waveform that goes in and then goes off in a ramp. And here the low moment, you can crank it up more, and it stays on. So different kinds of waveforms. It's very important to know exactly what this input waveform is, and also what the ramp cutoff is, and what the time channels are with which you're measuring something. And notice that different systems, here's a VTEM system. Here's the input current that looks like this. So it's got a much shallower ramp, and it's got a very different waveform. There's nothing really fundamentally different about these guys, but the details are really important if you're going to analyze the data and invert that. So one of the things that's an absolute must, if you get data from a contractor, you need to know exactly what this waveform is. You need to know exactly what time t equal to 0 is from those time channels. So we have a case history, and I'm going to do it. Because we're there. It'll just take 5 minutes. Here we go. So the case history, this is actually a very, I like this case history a lot for a variety of reasons. One is that it is relevant to many problems that we have today from the point of view of groundwater. The other is that it uses geophysics in a way that I think is very futuristic and responsible. And it is as follows. So the setup here is that we've got a region in Denmark, and what the groundwater hydrologists really want to know is, okay, suppose I put a well in here, and I start to draw the fluids out, right? I'm drawing water out, okay? Where's it coming from? Yeah, Esmeralda, here. Where's the water coming from? That's an important question. The second is, if I have another well over here, and I'm drawing down here, is that going to be drawing on the same source? Are these two wells connected? I mean, those are challenging problems. So geophysics has a role to play in that. And the way it's going to do it is to take the electromagnetic geophysics, help in using that to help generate a geologic model from which you actually make a hydrogeologic model. And then you can take that and put it into a mod flow or some algorithm to calculate where the water would go and what the gradients are. And then that can actually help solve the problem. So geophysics is sort of kind of like an intermediary there that provides important information, but in itself solve the problem. So here's what we're up against. So we've got basically clays at the bottom, and then you've got these channels that are in size. And these channels are filled with glacial sands, stuff like that. And importantly, they're pretty resistant. So what you're looking for are these channels here which are resistive, and the regions underlining here are these Miocene clays that are really conductive. So we've got clays out here that are maybe 1 to 10 ohm meters, and we've got these upper region channels that are maybe 60 ohm meters or more. So basically, using the EM geophysics to try to find the bottom of these channels. So right up against it. So that's a good use, right? You're trying to find basically a resistor over a conductor, and trying to find the surface of that conductor is kind of like a well-tuned problem. So the system you're going to use is that SkyTemp system, which I just talked about. Both the high moment and the low moment are used. And the data area are like this. So the blue lines are the lines where the data were collected. And some of it had to be removed because of cultural noise. I mean, you're flying over a region that's heavily populated. And you now take these, but you still have a lot of data soundings to be worked with. So each sounding that you have is going to be inverted. And there is still like just about 10,000 soundings. And each one of them was inverted in terms of just one dimension. But it was done in kind of like a quasi 3D environment, so that if I'm an inversion here, I'm not totally divorced what's happening in Esmeralda. They're somehow connected, make sure that there's too much variation. So it's called quasi-static approach. And the bottom line was that after doing that inversion, then you get essentially a 3D resistivity model. And if you did a depth, a slice of that at 5 meters above sea level, you see that the resistivity, so the reds and the purples are very resistive. So there's regions in here that are really quite resistive, and there's blues out here that are not. Remember I said what we're really interested in was the depth to the top of the clay. So that's what's here. So here's the depth to the top of the Paleogene. So this is mean elevation above sea level. So the blue is really deep, and the red is high. So you can see that there's these channels that are going through here. So in fact, there was about, after looking at this, they kind of came up with, well, there's sort of about 20 of these valley types of structures. And that was, so they're able to kind of use that to kind of make a geologic model of what was going into there. Then the next step was to take the results from the inversion, where you had conductivity or resistivity basically between 60 and 10, and to use borehole information to try to make a bit of a proxy between lithology and electrical resistivity. And that actually allowed them to generate a 3D hydrogeologic model. Okay? So now you've got a 3D cube in which each cell has got a hydraulic conductivity that's attached to it. Okay, now once you got that, then you could put that into ModFlow and then predict what's going to happen. So here they were withdrawing water here, and they were withdrawing water here. So when you look here to see, I'm drawing up here, so where's it coming in? It's sort of coming in from along that valley. So here's where that water's coming from. You draw from here, it's coming from there, and maybe they're almost touching. This is the kind of thing that is really, really useful to people, right? Because now they can start to make predictions. They can look to see, if I draw stuff out here, or I pump stuff in there, where is it all going to go? And geophysics, in this case, plays a really important role. So I think that's it. Let's break for lunch. We're a little bit late.
What time do you want to be back?
We should be back maybe 1:45. Is 3/4 an hour, or how long do you need for lunch? An hour? Okay, we'll see you at 10 to 2.
Hi. So I didn't make my check-in at 9 o'clock because I arrived a little bit later.
No problem.
Okay.